So recording is now on. And yeah, I'd like to welcome everyone to FRIDA 2021. Thanks everyone for joining. Thanks a lot to the speaker for accepting our invitation. And so we'll have 2 days. So first day on Monday and then on Friday. Each day has 4 talks with a break, 10-minute breaks in between and in the middle. So some participants, some speakers will give live talks, while others will have pre-recorded talks, but should be there to ask questions after the talk. So if you want to ask questions during the talk, you can use either the FRIDA stream on Zulip or the chat here on Zoom, or I guess you can just raise your hand also in Zoom if that's possible. I'm not sure, but it should. And yeah, I think that's pretty much it. Unless Sven, is there anything else you want to add? It's not.
No, I think we're good to go.
Great. Okay. So we're going to start with our first keynote speaker today, who is Julian Ross. So Julian just started as a tenure track faculty at the CISPA Helmut Center for Information Security. So Julian, the floor is yours.
Okay, let me just share my screen. Can you see my screen?
Yes.
Okay, great. Okay, so thank you for the introduction. The title of my talk is Formal Security Guarantees for Distributed Consensus Algorithms. And so now I realize that this workshop is maybe not all about consensus algorithms. So maybe let me start off with a little bit of a motivation for why we like to study these algorithms. So the motivation that I want to give is cashless payment systems. Okay, so suppose maybe that you're on your way to work and you stop by Starbucks to get a coffee. Okay, and now if you're living in an urban area, then chances are that you might be paying for this coffee using a credit card or a debit card. Okay, and what happens here is that you would authorize the bank or the credit card company to transfer a small amount of money from your bank account to the bank account of Starbucks. Okay, and once Starbucks verifies that this transaction has gone through, you would get your coffee. And so what we're doing here is implicitly making a trust assumption toward this bank or the credit card company to handle this payment in a secure way and to transfer our money to the bank account of Starbucks, right? And more than that, we're also paying the bank or the credit card provider a small fee to do this. Okay, so neither of these two things is very desirable. And for this reason, an approach which has gained a lot of attention over the last couple of years is whether or not we can actually replace this single authorized credit card provider or bank by some distributed protocol which emulates this central authority. Okay, so instead of placing all our trust in one central authority, the goal here would be to emulate this trusted authority using some distributed protocol that is run among all the users in the network. And instead of having this one single trust assumption, we would replace the single trust assumption by trusting that some majority of the parties that are participating in this payment system are acting honestly, say maybe half of them or 2/3 of them. Okay, so that's the idea. And the way that we would try to implement this is roughly the following. So we would like to construct some public transaction ledger, which all parties agree on. We also like to call this a blockchain because you can see it as a linked chain of blocks where every block keeps a bunch of transactions of the form Alice pays $5 to Starbucks, for example. Okay, and because everybody agrees on this public transaction ledger, users in the system can compute each other's balances from this public transaction ledger and see how much money everybody has. Okay, so now let's actually have a look at why it's so important that this ledger is a public ledger and everybody agrees on it. Okay, so why that's a really crucial feature. And so let's consider this really, really simple example here, where we have on the top the view of Bob and on the bottom the view of Charlie. Both are users in the system, and in the view of Bob, we have some transaction of Alice in one of these blocks, where Alice spends $5. Okay, and now the issue is that if Charlie down here has another transaction, say TXA hat, also of Alice, where Alice also spends $5, then effectively Alice gets to spend these $5 twice. Okay, maybe she buys coffee at Starbucks with the transaction on the top and the hot chocolate with the transaction down here on the bottom. And of course, this is double spending and it should be prevented in any reasonable cash system. And the easiest way to do this is by simply agreeing on a common view, which prevents such transactions which exist in the view of only one party by definition. Okay, and this problem of agreeing on a common view is actually a very fundamental and well-studied problem in the area of distributed computing, and it's known as the consensus problem. And that's the problem that I want to talk about today in my talk. And well, yeah, so as I already said, the goal of this problem is for all the parties in a system to agree on a common output under some non-triviality conditions. And it was first formalized by Lamport, Shostak, and Pease in 1982. And since 4 decades, people have studied it under various different constraints, and it's still ongoing. And I think its relevance is more than ever because now we actually use it in things like multi-party computation, blockchains, and more. So the problem about these algorithms to achieve distributed consensus is that often they're very complex and they have error-prone analyses. And in this talk, what I'd like to cover is first, I'd like to give you a little bit of an introduction to distributed consensus. I'd like to talk about the problem statement. I'd like to talk about under what conditions you can actually solve this problem in a distributed fashion and what general techniques are. I'd like to also talk about modularity in protocol design as a tool to facilitate simpler proofs that are better to check and are less error prone. I also want to talk about the role of modern cryptography in such protocols, because I think it has become quite prominent in recent years. And finally, I also want to discuss all of what I'm saying a little bit in the context of formal verification. Okay, so now without further ado, let's actually get into it and let's start talking about how the problem of consensus is actually defined. And in this talk, I want to focus on a very simple variant of consensus, which is known as Byzantine Agreement. And in this problem, we have some n parties, which are connected by pairwise channels over a distributed network. Let's say there are n of them. And what they would like to do is all of them have some, say, binary input to a protocol. And now they're trying to agree using this protocol, which they run over these pairwise channels, on some common output. Okay, so that's their goal. But the problem is that the protocol that they're trying to run is being obstructed by some minority of key Byzantine parties who are corrupt and who can cheat the protocol in any way that they like. Okay, and for example, they could send false messages, they could send different messages to different parties to confuse them, just try to make it as hard as possible to agree on this common output. So this is the problem statement. And now let me make this a little bit more formal. So the concrete guarantees that we would like to achieve from such a protocol are twofold. The first one is called consistency. So this is very simple. It just says that no matter what the inputs of the parties are, the protocol should always output the same output for all the parties in the system. But of course, by itself, this would be a trivial property to achieve because you could simply hard code some output into the protocol and always have the parties output the single output. And that's obviously not what we want. So we need some kind of non-triviality condition. And this is what we refer to as the validity condition. So in the validity condition, basically we require that if there is already a pre-agreement on some value here V star, so everybody already holds the input V star, then the protocol should actually preserve this agreement and output V star as the output for all parties in the system from the protocol. Okay, and this property makes the problem non-trivial. And finally, we have a third property, which is very simple to explain, and it's just the property of termination. So at the end of the protocol, everybody should be able to output some value and shut off their machine. Okay, so these are the three properties that we generally require. So now the first thing that we really have to talk about when starting to formally analyze these protocols is the model of communication that we consider. And so generally, there are two interesting models of communication. The first one is what is known as the synchronous model of communication. And here, we assume that parties have synchronized clocks. So time runs approximately at the same rate for everybody, and they know that it does, and they have shared clocks, which show the same time for all of them. And if a party A sends a message M to a party B, then we know some upper bound on the maximum network delay, such that if A sends this message to B, then it is delivered after at most delta, this upper known bound on the network delay, many steps on their clock. Okay, so this is a very nice assumption, and we can design very robust protocols under it, but oftentimes it's actually not justified for, say, chaotic systems like the internet. And whenever this happens, we actually have to consider a much more relaxed model of communication, which is known as the asynchronous model. So in the asynchronous model, messages can be arbitrarily delayed, and moreover, we actually assume that the adversary here has full control over the network. So it can reorder messages, it can deliver them out of order, you know, it can basically do whatever it wants, as long as it delivers any message that was previously sent by an honest party. So it can delay them as long as it wants, but it has to eventually deliver them. That's the only constraint. And so now the problem in this model, of course, is that if B does not see any messages from A, then B cannot be sure whether A is actually not sending this message on purpose or whether the adversary is delaying it. So this is the fundamental challenge in this model. And of course, that makes it much, much harder to design protocols in the asynchronous model of communication. Okay, so here are some known results on Byzantine Agreement. In synchronous networks, so if we do not assume cryptography, then it is possible to solve this problem if and only if the number of Byzantine parties is less than n/3. And this is a famous result due to Lamport, Shostak, and Pease, who also introduced the problem in the same work that they showed this result in. Then if we actually do assume cryptography, the picture changes a little bit. Here we can solve the problem if and only if the number of cheating parties is less than n/2. Now let's have a look at how the problem behaves in asynchronous networks. So here, it will be possible to solve the problem if and only if t is less than n/3, regardless of whether or not you're using cryptography. That might actually be a little surprising. And there's also another result in asynchronous networks due to Fisher, Lynch, and Patterson, which says that you actually have to use a randomized protocol, which is not deterministic, because otherwise you could get stuck in an asynchronous network. Okay, so a little bit more detail.
Just one question, maybe, Julian.
Sure. Yeah.
If I may. So what kind of cryptography would you use to go from the n/3 to the n/2 bound?
Typically, we use digital signatures. That's the main tool we use. Yeah, I'm going to talk a bit more about that actually later. So yeah, but that's the main tool to use. Another one is secret sharing, or also public key encryption. Yeah. Okay, thanks. Sure. Well, anyway, I think I already said this. So this result claims that deterministic Byzantine agreement is actually impossible in the asynchronous setting, and this holds even if you only consider a single crash fault. So a crash fault is a benign fault which does not send any incorrect messages. It just stops sending messages altogether. And this result is extremely strong. It says, even if you have only a single such fault, your protocol can get indefinitely stuck. Okay, so it's very, very strong impossibility result, and it really limits what we can do in this asynchronous model. So in particular, it really means that randomness in the form of some coin flips are unavoidable in this model, and we'll see how that actually comes in. Okay. So another really important thing to consider when we look at these protocols is how we actually design protocols. And I think there are two general strategies to design protocols for Byzantine Agreement. One is sort of a modular design, where we prove the security of submodules separately, and then we put them together and show that from the properties of these submodules, we can build a more complex system which achieves the full thing that we would like. And the benefit of this is that it gives relatively simple proofs. I'm actually going to talk about one of these proofs a little bit later in my talk and show you how it behaves and everything. So they are not as hard to verify, but the downside is that modular protocol design often leads to less efficient protocols, because you're sort of, you're trying to reduce efficiency a little bit at the sake of simplicity, and this often costs you a little bit in efficiency. Now, the other thing that people have to do is non-modular protocol design. And basically, this just means that you try to prove the whole protocol at once. So you have one very complex protocol, and you just go through the whole protocol and prove everything, basically at the same time. And there are a lot of works like this also. And the benefit of this is that you can sort of design pipeline protocols which have really high efficiency. But of course, the downside is that the proofs become accordingly much more complex and also prone to error and much more difficult to verify. And what I want to talk about next is how modular protocol design can actually help a little bit. It can make it, for example, possible to explain how to build such a Byzantine Agreement protocol to you in a couple of minutes. But on the other hand, it's not really a solution to everything, as you will see, because there are still a lot of subtleties that can arise if you put these submodules together, even if you can analyze their security properties in isolation. So yeah, let's jump right into it, and let's look at a key abstraction that we would use to build these Byzantine Agreement protocols. And this is sort of a weaker form of Byzantine Agreement, which we call graded consensus. So graded consensus works as follows. We consider sort of the same setting. So we still have n parties, and t out of them are Byzantine, and all of them, say, have a binary input to the protocol. And now, instead of just outputting one single value, as you would require in Byzantine Agreement, we actually weaken what the parties are outputting here a little bit by having the output be graded. Okay, so on top of your output, you actually also give a grade. I've denoted this grade here by G1 for party 1, G2 for party 2, and G3 for party 3. And this grade reflects your confidence in the output that you're giving. Okay, so the grade can be any value from 0, 1, or 2, where 2 reflects that your confidence is very high, and 0 reflects that you don't even have an output. So if you output grade 0, then it means that you don't know what the output is, you're just outputting the default value. And 1 is sort of in the middle, and it says, well, I'm not really sure about this output. Maybe it's good, maybe it's not so good. I'm not sure what the other parties are outputting. And this is what I actually want to formalize next, because we can sort of place consistency guarantees on these grades now in a similar fashion that we previously did for Byzantine Agreement. Okay, so more formally, we require 2 parts of graded consistency now. So the first part of graded consistency is that, suppose that there is one party, PI, which outputs the highest grade, basically. So it outputs value V with the highest grade 2. And now what we require is that all other honest parties output the same output, also V, either with the highest grade or with a grade lower, namely grade 1. Okay, but it cannot be that somebody outputs the lowest grade, 0, with no output. This we can guarantee. So this is the first requirement that we want from such a graded consensus routine. Okay, so here in my example, here in red, I drew what one possible set of outputs that you could get if somebody would output grade 2. So this is the first requirement of such a graded consensus protocol. So you can see it's a little bit weaker than what we get for Byzantine Agreement because we have these grades. But now we also have a second graded consistency property. And the second property that we would like is as follows. So suppose that there is an honest party that outputs a value v with grade 1. So it's like this middle grade. Then what we would require is that either another honest party would output the highest grade, namely 2, with the same output, or another party outputs grade 1 with this output, or somebody outputs the default value with grade 0. So all of these three things are possible. What is not possible is that somebody outputs the opposing output, namely 1 minus v, if we consider binary protocols, with a non-zero grade, either 1 or 2. Okay, so this is excluded in this second graded consistency property. Okay, so now that we have that, this is the consistency that we require from such a protocol. Let's go to the analogy of validity that we would consider in this type of weaker agreement primitive. So we call this graded validity, and graded validity is, as I said, the weakening of validity that we saw in Byzantine Agreement. Again, we somehow want to preserve pre-agreement in such a protocol. And so what we require here is that if everybody starts with the same input v star, then all honest parties should output v star together with the highest grade. Okay. So this is how we translate graded validity. And so now the main problem, if you look at this kind of protocol with these kind of guarantees, is that if you're a party and you output the highest grade, then you don't know whether another party has also output this highest grade, or if they only output the same output with grade 1. And if you're a party that outputs something with grade 1, then you don't know whether you're in the middle, or if there is a party that actually has a lower output with grade 0, and it's just outputting the default output. It doesn't know what you output. This is sort of the central difficulty and why it does not give you full agreement yet. And so we need to go from this abstraction to the stronger thing, which is Byzantine Agreement. And what we're going to talk about next is how to actually do that. That's the roadmap. So this is a really central abstraction, and it's used very often to prove these kinds of protocols. But even if you look at protocols which are written down in a non-modular fashion, you can somehow still find the structure in many cases. So you can kind of look at the protocol code, and somehow, even if it's implicit, you can still sort of abstract out this graded consensus routines sometimes in these non-modular protocols. And I think that's kind of a nice thing to observe. So now let's talk about how to go from this weaker type of agreement to the stronger type of agreement, which we actually want. And to do that, we will need something called a common coin. So what is a common coin? So it's a distributed routine. And basically what it does is everybody can invoke it. And what it outputs will be a coin, C, which is going to be the same for all parties that invoke it. Okay. And not only that, it should remain a random value before the first honest party invokes this routine. So it should remain unpredictable to the adversary who is somehow trying to keep the honest parties out of agreement until the first honest party invokes this coin and sees what its value is. And typically we can construct these kinds of things from cryptography, and I will actually talk about this a little bit later in my talk. So now, how to go from graded consensus to BA using such a common coin? So basically, the idea is to use this coin to break deadlocks where parties would be kept out of agreement indefinitely. And this is an idea that was originally proposed by Rabin in 1983 and later refined by Feldman and Mikhaly. I think Ben Orr also had some ideas here. He has a famous paper. Actually, I failed to mention him here on my slide, so I'm sorry for that. These are the papers that I typically think about when I consider this paradigm. So this is basically the outline, and a nice thing about this is you can use it in the asynchronous model to get agreement protocols. So this definitely works there. But you can also use it in the synchronous model to get very, very round efficient protocols, which terminate in an expected constant number of rounds. So this was actually the work by Feldman and Mikhaly who first showed how to do this. Now, the details of how you actually go from graded consensus to Byzantine agreement using this coin really depends on the model of synchrony. And that's what I want to go through next. To give you somehow an idea of how these protocols work and what the difficulties are when we try to prove them. Okay, so let's look at the main idea. So we have this graded consensus routine. We assume that it's secure in the sense that it satisfies these three properties that I showed you: graded consistency 1, graded consistency 2, and graded validity. And now we want to do something with it to get from this weaker abstraction to full Byzantine agreement. Okay, so how do we do that? So I'm going to consider the view of one honest party here, which starts with input V, and it's going to set an iteration value V0 to this initial input value V, and it's going to input this to the graded consensus routine. And now the graded consensus routine will output some value V1 along with a grade G1 after the first run. And what this party will now do is it will use whatever the graded consensus routine output as the input to the next iteration. So it will rerun the graded consensus routine with this output from the first iteration. Okay, so now it gets a second output and it just keeps doing this. And my claim is that as soon as somebody observes the highest grade 2 in some iteration k, then this output that you saw together with this grade 2 will always be the output for any further iteration. So why is this true? Well, because if you output grade 2 in some iteration k, then you know that everybody else output the same value bk as you did, because that is what graded consistency 1 said. If you have the highest grade, then everybody else would have to have this grade -1 at least with the same output. And so now everybody inputs the same thing to the next iteration, and now we can use graded validity, which says that if everybody inputs the same thing, you should have this value with the highest grade in the next iteration. And now everybody just keeps inputting the same for all future iterations by induction. So the loop converges once you first see it outputting the highest possible grade. Okay, so but actually this doesn't quite work yet. And why doesn't it work? The reason is that in, say, the first iteration, you could actually output the default value with grade 0. And now it's actually not clear what we would input to this iteration here to the next iteration of the graded consensus routine, because the graded consensus routine only takes binary inputs. And this default value is not a binary input, so we cannot feed it to the next iteration if that is what we see after the first time graded consensus outputs. So what do we do instead? Well, instead, we would actually flip this common coin, and this would give us our value V1. And V1 would be the value that we input if we didn't get a proper output from the first time where we ran graded consensus. So we input this to the graded consensus routine to run it a second time. And my claim is that with probability at least 1/2, everybody would input the same value V1 to the second iteration of the graded consensus routine in this particular case. And if this were actually to happen, then you would get convergence immediately in the second round already. And more generally, you would get it in round k with probability 1 minus 2 to the minus k. So why is this true? Let's have a look at the following setting. So we have a party P1 on top here and a party P2 on the bottom. And they're running this, this loop. And what I want to look at now is a situation where the party on the top does not output grade 2. It outputs grade 1 along with some value. And I want to look at any possible combination of another output by the party on the bottom. And I want to argue that no matter what these two outputs are, the probability that they agree in the next iteration will always be at least 1/2 when they rely on this common coin. So let's try to see that. So my first example here, let's look at what happens if the top party here would output some value v with grade 1, and the bottom party would output the complementary output 1 minus v, also with grade 1. But note that this is not possible because it would violate graded consistency 2. You cannot output different outputs with a non-zero grade. Okay, so this is not possible. The second case is if the top party here would output V with grade 1, and the bottom party also outputs V with grade 1. But in this case, we're fine because both of the parties would input the same value to the next iteration. So this is not an issue. Here, nobody would pick the coin, right? So the third case, and I think this is sort of the most interesting one, is where the top party outputs grade 1 along with value V, but the bottom party outputs the default value with grade 0. In this case, the bottom party would actually go for the value of the coin for the next iteration. And so now the crucial thing here is, and here we're actually using the synchronous model of computation, that the parties can wait until they can be sure that everybody terminated this graded consensus routine because it runs for a fixed number of rounds. So they can wait until it terminates for everybody, and then they can invoke the coin flip. And so now we can be sure that the coin flip does not depend, or more precisely that whatever parties output in the graded consensus routine does not depend on the coin flip, so the adversary cannot bias it. And for that reason, the coin will actually agree with this value V, which the top party output here with probability at least 1/2. In that case, you get convergence whenever this happens. Okay, so I hope that this was convincing. Okay, so now that we, oh, actually, there's one more trivial case. This is where everybody outputs grade 0. But this is actually very easy because now everybody goes for the coin in the next iteration, and the coin always agrees for everybody. So in this case, also everybody would input the same value to the next iteration. That's actually a simple case.
So just one question.
Sure.
So what would happen if this was asynchronous? How would the adversary be able to bias the coin?
Oh yeah, so actually, I'm going to discuss that after showing this example.
Okay, great.
Yeah, so, but thanks for the question. So yeah, I haven't forgotten about that. So let me do that in after finishing this one.
Okay.
So there is one more subtlety, and this is actually going to be another thing that we have to discuss when we go to the asynchronous model, which is how to break from this loop. Okay. So why is this difficult? Let's actually take a little bit more of a deep look into this. So suppose that, again, we have these two parties, and now you observe that you have the highest grade, and then you want to terminate from this loop because you don't want to keep running it forever, right? This would violate the termination condition. At some point, you do want to get your output and you want to shut off your machine. You want to stop computing. So a very naive strategy would be to observe this grade 2 for the first time in some iteration k, and then just halt the protocol, not participate in any further iterations. But this is problematic. And why is it problematic? Because the party on the bottom here might actually not have seen grade 2 in that iteration. It might have only seen grade 1 in the same iteration. And if this happens, well, the top party does not participate in any further iterations, but the bottom party does. And if the bottom party participates in a further iteration of the graded consensus routine, then because now not every honest party is participating in this graded consensus routine anymore, we effectively get a dishonest majority in that graded consensus routine. Potentially, it's not clear, but it might happen. And in this case, it would lose all its security guarantees. And now, of course, we cannot be sure that P2 would ever output V with grade 2 in any of the subsequent iterations. And then it might never get to halt. And this is a problem. So how do we safely break from this loop? So here's the idea. Let's say we're in iteration k-1, and now after inputting vk-1 to the graded consensus routine, we see vk with grade 2. It's the first time we see grade 2. Then we run exactly one more iteration with this value vk, and then we halt. But importantly, we actually don't care about the output of that iteration. So we completely ignore whatever the graded consensus routine would output in the final iteration. We just stick with the value vk, which we saw in the prior iteration. And that's going to be our output. And the intuition behind this is that we can actually help the other parties that are participating in this graded consensus routine or in this loop to terminate also. And I can maybe illustrate this a little bit better again with this two-party view here. So if two parties are running this loop, then on the bottom, let's say the top party is the first one, again, to output grade 2 for the first time, and the bottom party would output grade 1. So now the instruction is that both parties would run the graded consensus routine the next time. And now the top party, after running it again, would halt. Okay, and because of the graded validity condition, we know that the bottom party now also sees grade 2, because in this iteration, everybody input the same thing to graded consensus, right? This is the convergence that we were talking about. So now what happens is that the bottom party actually runs one more iteration. And in this iteration, it could happen that the graded consensus routine that we're running might become insecure because not everybody is participating in it anymore. So it could lose all security guarantees. But this actually doesn't matter, because we said that the bottom party here ignores whatever comes out of the last consensus iteration. It already picked its output when it saw it with grade 2, and we know that that run of the graded consensus routine did remain secure. So it doesn't matter what the last graded consensus routine outputs here, as long as it terminates. And this is actually another property where we do rely on the synchronous model of communication, because here we can really abort the protocol after a fixed number of rounds and be sure that everybody gets their output in this protocol. Okay, so here we do actually require it a second time. So this is how you securely break from the loop in the synchronous model. And as you can see, it's already quite non-trivial, even though the protocols are sort of designed in a modular fashion to break from them in a secure way and to really argue that this remains secure. And now we will see that if we go to the asynchronous setting, things even get a little bit more contrived. So let's have a look at that. So again, let's attempt to do our loop here. We start the same way. We input this value that we use as an input value to the first graded consensus routine that we run. We get some output, and if it's the bottom value, we would try to flip a coin. But the problem is, and I think this was exactly the question that somebody asks, when would we actually flip this coin? This is an issue, because if we attempt to flip the coin too early, then it might be that somebody is still running this graded consensus routine while we're flipping the coin. And this is an issue because now the adversary could bias whatever that party who is still running the graded consensus routine could output. And the reason that this is possible is that in the asynchronous model, we do not have any clocks, we do not have any time. So it's possible that parties can drift apart or fall behind. And this is sort of the central thing that we have to deal with when we consider the asynchronous model of communication. So in a little bit more detail, let's actually look at this two-party view again. And on the top, we have party 1 input B01 to the graded consensus routine. On the bottom, we have party 2 input B02 to the graded consensus routine. And now let's suppose that the bottom party here gets the default output with grade 0. And now it would go for the coin. And so what the adversary now does is it would observe this coin, okay? And if we make no further security assumptions about this graded consensus routine, what the adversary can do is it can bias the outcome of the above consensus routine to be exactly the opposite value of whatever the coin output. Okay, so there's no violation in graded consistency in doing so because the bottom party output the default value. So the party up here can output anything. And if the adversary can bias the outcome, then it can actually make it so that you would never reach convergence in this way. And again, for many consensus routine, for many graded consensus protocols, this is actually not possible. I do want to stress that, but it is an additional security assumption that we have to make about this graded consensus routine. And it's not clear that any graded consensus routine actually satisfies this additional assumption. So we cannot just make it. Okay, so now that being said, what can we actually do to still get this convergence and eventually terminate from this protocol? This is what I just said, basically. So the attempt that we're going to do is to not use one graded consensus routine, but actually use 2 graded consensus routines per iteration. And here's how that would work. So again, we start with our initial value. We input this initial value to the first graded consensus routine in the first iteration. And now this first graded consensus routine would output some intermediary value. They call it V tilde here with an intermediary grade, G tilde, and we will check if G tilde equals 2, the highest grade. And so if it does, we would use V tilde as the input to the graded consensus routine, which we run next. And if not, we would flip a coin and use whatever comes out of the coin flip as the input to the graded consensus routine that we run for the second try. Okay, and then whatever comes out of the second graded consensus routine is going to be the value that we use for the next iteration. By the way, if this value here is the default value, then we would just stick with the coin as the input for our next iteration. So we only use it if it is a binary input. So why does this work better than if we just use a single iteration? So let's have a look at that. So the idea is that, again, considering this two-party view, that, let's again say that the top party inputs V01 and the bottom party inputs V02. The idea is that for any possible combination of outputs, the adversary cannot bias whatever comes out of the top graded consensus routine here. So let's go through the possible combinations to see why this is true. So say the bottom party outputs the default value with grade 0. In this case, it would go for the coin. Now the adversary would try to bias whatever the top party outputs here, but actually it cannot bias whatever the top party will pick to input the next graded consensus routine. And why is this true? Because if the bottom party outputs 0, then the top party has to output grade 1, because otherwise there would be a violation in the graded consistency 1 property, which says that if somebody outputs grade 2, then another party has to output grade at least 1. And if both parties output not grade 2, then both of them would go for the coin flip. So in this case, both parties would input the same value to the next graded consensus iteration. Okay, so let's have a look at what would happen if the top party here would output, or the bottom party more precisely, would output grade 1 with the value V2 tilde. In this case, it would still go for the coin because our new instruction says that you always go for the coin if you don't have the highest grade. So now what would happen if the adversary observed this situation and attempted to make the party on the top here output some value with the highest grade, grade 2, because in that case, the party on the top here would not go for the coin. And in this case, you could potentially bias what comes out of this protocol and make it intentionally not agree with whatever this coin flip is. But interestingly, the adversary here has no way of biasing this output either. And why is this true? Because the bottom party has a fixed output. This is V2 tilde. And by graded consistency, we know that the top party must actually output the same value here as the party on the top. And that means that once the party on the bottom has output their value and decides to go for the coin, the adversary can no longer bias whatever comes out of the graded consensus routine for anybody else. And because of this, in this particular way of constructing the protocol, the adversary has no advantage in biasing the outputs from this first graded consensus routine either. And that means that in any iteration with probability 1/2, we actually get to a point where you converge in the next iteration because all parties would input the same value to the second graded consensus routine with probability at least 1/2. Okay, so now we're almost done, but we have to still discuss how to break from this loop. And it's actually going to be a little bit more difficult than what we had in the synchronous model, because now we again have these race conditions that come from the asynchronous model of computation. So now suppose again that you have a party here that sees the highest grade in some iteration k for the first time, and now it just decides to halt. Now, of course, we already discussed that this could lead to a problem, but interestingly, it's not the same problem as what we previously saw. So what is the problem now? So now the problem is that you could get stuck. It does not mean that you would lose security or that you would output an incorrect value. It just means that you cannot get any value. So what would happen? The first party on the top here would output grade 2 with some output, and it would decide to halt. And now it might just be that the second graded consensus routine for another party on the bottom here loses all termination guarantees that we can only guarantee if we have some honest majority, and it might never output. But interestingly, and this is different from the example that we looked at in the synchronous model, the graded consensus routine here on the bottom cannot lose any security properties beyond termination if all the honest parties do is just halt and not participate anymore. And why is this the case? Well, because it's an asynchronous graded consensus routine now. And in the asynchronous model, you always have to be able to tolerate parties not sending any new messages without losing security properties, except of course termination. And this is true because the adversary could always delay some honest parties' messages, and of course the protocol should remain secure in this case. So all that can happen here is that you could potentially get stuck. And this is actually something that we can use to still get to an output in this case. And what we'll use to do this, very, very simple solution, is actually something called signatures. Okay, so signatures, if you're not familiar with them, allow you to cryptographically sign a message. And the way that they work is basically as follows. So every party in the system, say PI, holds a secret key, which we denote as SKI, and a public key, PKI. So only the party PI will know its own secret key, but everybody will know its public key. And using its secret key, it can create a signature on a message, which we denote as this pointed bracket subscript I. And now unforgeability says that without the secret key of this party, it's not going to be possible to forge this signature. However, using the public key, everybody is able to check that this is a valid signature on the message under the secret key of this party. This is all the syntax that you need to know. And now using this cryptographic primitive, let's actually have a look at how to securely break from this loop, even in an asynchronous world. So here's how to do it. You run the protocol until you first observe grade 2. In that case, you would sign whatever value you output using your secret key, and you send it to everybody in the network. Okay. And so now what you do is you keep running these graded consensus loops, and you gather signatures from other parties until you see T+1 many signatures on whatever value you output yourself from this graded consensus routine in which you signed and sent to everybody. And you know that this is eventually going to happen because either you were the first party and you signed the message and sent it to everybody, and because you keep participating, everybody will get to that same point eventually and also sign the same message and send it to everybody. So eventually you will accumulate T+1 signatures because there are always at least T+1 honest parties. On the other hand, you know that you will never gather a false list of T+1 signatures because nobody, once you output this value from the graded consensus routine, would ever output something incorrect, because the protocol guarantees that once you converge on some value, this will always be the output of any honest party that ever outputs with the highest grade. And here we implicitly actually use that even if some parties terminate early, this cannot cause other parties to output incorrect values from this graded consensus loop, because these protocols have asynchronous security properties, so they cannot lose them if parties simply do not participate anymore. So anybody who will ever sign anything will sign this message and send it to everybody. So now if you observe such a list, what you will do is you will send it to everybody and then you will halt. And why does this work? Because once you send it to everybody and you halt, you know that everybody will receive this list of signatures eventually. And in that case, they can also send it to everybody and then halt. So you basically propagate a certificate of being able to halt. And this is how you securely break from this loop using cryptography in the asynchronous setting. Okay, so now this was a pretty complicated example for such a simple paradigm. And the lessons to learn here is, I think, that compositions of sub-protocols is a very subtle thing. It doesn't just follow in a black box way. And protocols might not behave as expected when you combine them. Okay, and this is something that you really need to watch out when proving these protocols and doing these proofs. One very nice thing that we tend to use in cryptography are composable frameworks. And in such frameworks, what we have is basically a composition theorem that allows us to prove submodules in this framework securely, and then later to combine them. And the composition theorem says if you combine two secure things, then whatever comes out of it will still remain secure. So examples of such frameworks are the universal composability framework by Canetti or the constructive cryptography framework by Mauva. Okay. So now let's actually, in the last part of my talk, have a look at some of the modern cryptography that is used today to construct these protocols. So I already talked about signatures, but other types of cryptographies are also used. So signatures are typically used for authentication or certificates, as in the example that I showed you. Encryption is used for privacy, and things like threshold signatures or verifiable random functions are used for coin flipping. And a central question in this area, of course, is how to model cryptography when we prove such a protocol secure. And the main tool here is the so-called DolfYao model, which was proposed by DollarVR in 1983. So this model kind of abstracts away instantiation-specific properties of the cryptography that we use, and it treats cryptography as an idealized and symbolic primitive. And so as an example, we can look at signatures, which in the DollarVR model are basically treated as follows. So if a party PI is not Byzantine, then its signature is perfectly unforgeable. Okay, so we just treat it as a symbolic object, which has these perfect security guarantees. But of course, we know that because signatures are public key primitive, this is actually not possible to achieve in reality. So this is an idealized model, but it's very convenient for proving security statements in such protocols, because usually this is a close enough abstraction. But now if we look at something like a threshold signature, which I'm going to explain in a little bit more detail now, we can see that this model does not always hold up with more modern cryptography. Okay, so in a threshold signature, every party PI holds a secret key share. And you can use the secret key share to produce signature shares. There's a fixed threshold T, usually set to the corruption threshold of the Byzantine Agreement protocol that we're using this in. And any T+1 signature shares, which you can create with these secret key shares, will give you a unique signature on a message M. So whatever T+1 shares you combine, they will always give you the same message M. This is actually a crucial property which we can exploit to do things like coin flips and such, and I will show this on the next slide. Another property, which is very crucial here, is that any fewer than T+1 shares give absolutely no information about the combined signature on M. So in order to use these things, we usually assume the existence of a trusted dealer that distributes these key shares at the onset of the protocol. And this is something that you don't need to do with classical signatures. There, everybody can create their own keys. So this is a stronger assumption that we rely on here. So here is sort of a pictorial description of this. So suppose we have 7 parties and the threshold is set to 2, then any 3 of them would give you this unique signature. You could either take these 3 or these 3 or these 3. And all of them combined would always yield the same combined signature. So how can we use this to flip coins? Well, to flip the kth coin when running a protocol, the party PI would do the following. So it would sign the integer k, and then it would broadcast this signature share to everybody. And it would wait to collect a set of T+1 shares from other parties. And once it obtains these T+1 shares, then it can combine them into a combined signature and extract whatever entropy is in this combined signature using a cryptographic hash function, which I denoted here by H. And this, what comes out of the hash function, will give you the kth coin. Okay, so the threshold ensures that the kth coin is unpredictable until the first party actually participates in this coin flip by sending its signature share on this value of k. And also because the signature on k, the combined signature, is unique and always the same, no matter which T+1 shares you combine, whatever comes out of this hash function will always be a unique value. So everybody always agrees on it. And these are 2 very, very nice properties that threshold signatures give you. So now let's actually have a look at how these things hold up when we consider them in the DollarVR model. So the problem with this model is that it takes away all non-symbolic properties of cryptographic primitives. So how are we supposed to model something that's supposed to look random? If we just treat it as a symbolic object, then it has no random properties by definition. And of course, this is a crucial property for something like a threshold signature or a verifiable random function, which we use to flip these coins in these protocols. And it seems because of this that the DollarVR model is incompatible with randomized protocols that use these types of cryptography to flip coins. So how do we get around that if we would like to prove such a protocol secure? Well, what we can do is we can actually consider how these protocols actually look. So a little bit simplified, how to flip a coin via threshold signatures, how these threshold signatures actually work are as follows. So the trusted dealer would create a random polynomial, meaning it picks random coefficients, and it picks some random polynomial of degree t over a field fp of prime order. And now the dealer evaluates this polynomial at some fixed points alpha I, and it gives q evaluated at this point alpha I, let's call that point si, to the ith party. And now any t+1 parties can together interpolate this polynomial q, and they can evaluate it at the point 0. And if we set point 0 to the coin, then we can actually flip the coin in a way that is not predictable by the adversary. This is a little bit simplified, but basically these are how these threshold signatures work. And the main observation here is that once the dealer actually shares all of these shares to the parties, then everything else that you're doing is completely deterministic. So all the randomness is actually pushed to the trusted setup done by the dealer, and everything else is just deterministic because you're just combining these shares, and the polynomial that comes out of it is completely determined by whatever the dealer gives you. So is this a violation of the FLP result? No, it's not, because FLP actually says nothing about when the randomness is generated. Okay, and so here the dealer just generates all the randomness in this initial setup step. And the question, of course, is whether or not this simplifies or helps with formal verification. So that's not completely clear, but here is a very, very rough strategy of how you can actually verify such a randomized protocol that uses threshold signatures. It's just a blueprint, but here is an idea. So you can pick the code of the adversary A. This might be a randomized routine. And now you can securely generate the keys of the parties in this protocol according to the key generation procedure. This is a randomized procedure, of course. And then you can repeat the following steps. So you would pick specific random coins for R uniformly at random. Then you run the code of this adversary A that you've picked, and you verify whether, now everything is completely deterministic, you verify whether this particular choice of random coins and this particular choice of keys leads to an insecure run. Now you keep doing this many times for many, many different choices of R, but you always keep the keys fixed. And now if only a small fraction of different coins that you're trying this for will lead to an insecure run of the protocol, then you would consider the protocol secure. Okay, and now of course you need to repeat this over all possible strategies that the adversary A could have. And now you would basically fix a new adversary, then generate new keys and repeat the adversary over many runs with different random coins. And again, you would see whether or not it leads to a secure or insecure run for a large fraction of these runs. So this is like a very, very simplified blueprint, but I think this is really where it can help, that everything inside these protocols is completely deterministic once the keys are set up. So you don't need to consider any further randomness inside these keys because everything is just completely deterministic. So now, is it possible to generalize this concept if we just view any randomized protocol as a deterministic protocol that takes as a second input, some random coins? So again, we would fix an adversary A here, then we would fix random coins for the parties. And then again, we would repeat many runs of the adversary with different random coins for the adversary specifically, but where we leave the random coins of the honest parties the same over all of these repetitions. And then we would repeat the whole step for different strategies of A. And then again, we would consider a protocol secure against one particular strategy of the adversary if only a small fraction of these coins lead to an insecure run. So a problem with this generalization is that now it basically assumes something about how these random coins are used inside the protocol. And the problem is that if we do this, then there are certainly examples where the use of these random coins would lead to an insecure run. One prime example is if the protocol itself uses pseudo-random number generators to expand randomness, for example. So here it really depends on how you implement these subroutines, the pseudo-random number generator, which is being used in a protocol. And of course, in a general protocol description, which we would look at and verify, it's not specified how these pseudo-random number generators would actually look, or a hash function or whatever. So this is a crucial difference to the setting where I showed you how to do it for threshold signatures, because there all the randomized subroutines, seemingly randomized subroutines, are fully specified by the cryptographic code of these subroutines. So it's not clear whether or not this approach can easily be generalized to verify randomized protocols. So here are some takeaways. Formally verifying modern consensus protocols is difficult, even more so if protocols are randomized, because you can run into all of these different issues that I showed you in my example. Modular protocol design can definitely help, but it is not a panacea. I think some important next steps might be to try to explain some existing protocols like PBFT, for example, in a more modular fashion, because these protocols are typically very high performing, very streamlined protocols, and it's very difficult from somebody who's not intimately familiar with them to check their correctness, because they're so pipelined and so high performing, and that's the way that they're written. So explaining them retroactively using a more modular design might actually be very helpful to improve understanding for them. And second, another nice step might be to refine the DollarVR model to also allow to model some of these newer cryptographic primitives and not be sort of a purely symbolic model, but also integrate some sort of probabilistic guarantees, which we might be able to use to analyze these randomized protocols that use things like threshold signatures or verifiable random functions in a more easy to use fashion. Okay, that concludes my talk. Thank you. If you have any questions, happy to answer.
Yeah, thank you very much for your talk. It was very interesting. We might just have time for one or two questions at the moment, but we'll also have the discussion session after the talks today, where we'll be able to ask more questions. So,
sure.
If anybody has one or two quick questions?
May I? Can you hear me?
Igor has a, yeah.
So kind of a naive question. You have this trusted dealer, right?
Yes.
But it means you have to trust the trusted dealer, right? Because why cannot you just say that the trusted dealer decides on your value and that's it?
Okay, so that's a very good question. The reason that this is not this doesn't trivialize the problem is that you only have to trust the dealer at the very beginning of the protocol. So it sets up the keys once, and now you can run an arbitrary number of Byzantine Agreement protocols essentially without the dealer ever coming online again. So it's a one-time thing, and you never have to trust it again after that, right? And what you're proposing is basically that the dealer would have to be online all the time and help us evaluate any Byzantine agreement securely.
Makes sense. Thanks a lot.
Sure.
So maybe another quick question from me. So you presented this method for verifying randomized protocol, which kind of pushes the random inputs as input to a deterministic protocol.
Yes.
And so do you know of applications of these methods where protocols have been formally proved, maybe like sincere prover?
I've never formally verified a protocol, but I think this is a general strategy that might help to do it. Because if you're verifying a protocol and you're trying to do, for example, a proof by induction, right, and you have to argue about probabilities when you're doing the verification, I think that really complicates the proof. But if you have a completely deterministic protocol where everything is fully determined by whatever coins the adversary has and by whatever values are input to the honest parties, then I think exhaustive verification might actually be a lot easier than proving something like an inductive statement.
Yeah, but the thing though is that so you have to quantify overall adversary strategies and
Right. I mean, what you have to do is but in some sense you always have to do this, right? Because even if you're proving an inductive statement, you still have to quantify overall possibilities of what the adversary can do in every step. I mean, you don't get around that. The only thing that this helps you with is that you can take any randomized component out of this inductive proof and you can put it at the beginning of the protocol. So it's not going to show up in your inductive step anymore because of this.
I mean, if I remember your slide correctly, you also have to somehow count that the bad executions are.
Yes, because okay, so actually, you can go back to that slide. Let me just. Yeah. So the idea is, right, that what do we mean when we say the protocol is so none of these things are perfect, right? Usually we can only say something with high probability. Right. So what we mean here is that for a large fraction of random coins for the adversary, so the probability really goes over the random coins of the adversary here, the protocol would remain secure for any choice of these keys that we make. Okay, so what we could do is, for example, we could repeat this step for 1,000 different choices of random coins for the adversary A. And if the protocol remains secure for 990 of them, then we know that the protocol achieves security with 99.9% probability.
I see. So if I understand correctly, you're going to take a kind of a sampling approach where
yes,
there's actually going to be random choices in your verification procedure.
Yes. And I don't really see a way around that if the protocol only achieves agreement with high probability rather than perfectly. But this is typically the guarantee that these consensus routines give you, right? It's not, well, actually, it's not completely true. There are also Las Vegas type consensus routines, which actually do give you agreement with 100% probability. But for many high-performing algorithms, which are actually considered in the literature, we have Monte Carlo type algorithms, which only give you agreement with a high probability, and this is what we mean here. So the probability goes over the random coins of the adversary.
Okay, yeah. I understand. Thanks.
Sure.
Okay, well, thank you again for this very interesting talk. I think it's time to switch to the next talk.
No, stop my sharing.
Yes, thank you. All right, so our next speaker is Joseph Tassarotti, who's faculty at Boston College, but also affiliated with MIT. And he's going to talk about the modular verification of distributed systems with Grove. Joseph, the floor is yours.
Today I'll be talking about Grove, our new framework for modular verification of distributed systems. Now, as I'm sure you're all aware, oftentimes when we think about distributed systems, we model them as state machines. Now, this abstraction has been enormously successful, everywhere from the way that theorists design and think about the protocols that they come up with, to the way that implementations are sometimes organized, and perhaps most relevantly for this audience, the way that we carry out verification. However, there are other aspects of implementations of distributed systems that lie at the periphery of this abstraction, or in some sense fall outside of it. As an example of some of those things, we can think of composing together distributed systems that might be built out of smaller pieces, or sometimes we might be interested in distributed systems where within a node we might have shared memory concurrency. And finally, we often need to consider the fact that clients that interact with the distributed system have rich internal state and library code that may not be well reflected in the way we think of protocols as state transition systems. Grove is a new COC-based framework for verifying distributed systems that addresses these issues. It supports implementations of distributed systems in Go to give efficient code. And it's based on the Irish concurrent separation logic framework, which allows us to use powerful tools that have been developed for shared memory concurrency and bring them to distributed systems. In order to better explain the problems that Grove is addressing, I want to describe the key value server that we've verified using Grove. So in this system, there are a number of servers, here labeled A, B, and C in blue, a client in green, and a coordination manager. Servers handle different shards, that is, ranges of the key value space. So clients talk to different servers based on what key they're interested in. For example, a client might do a get operation on some key K1, which requires talking to server A. Server A will then respond to the client with the value. A request for a different key, say K2, might need to go to server B instead. Now, the key value service allows us to add new servers. So here a server D has come online and it wants to join the system, and it does so by sending a message to the coordinator, the yellow circle, saying that it wishes to join. In response, what the coordinator does is contact the other key value servers and tells them to send various chunks of the key value space to the new server D, thereby rebalancing the distribution of shards across the different servers. They then individually send each of those shards as appropriate to D. Now, after this rebalancing has occurred, the green circle client might again ask server A for the value of key 1. However, as a result of the rebalancing, A may no longer have that key, and so it indicates this to the client. At that point, the client makes a query to the coordinator to ask where key 1 has gone, and the coordinator says, oh, it has gone to server D, in which case the client then forwards its request to D. To avoid having to query the coordinator every single time the client wants to do a get, the client will cache the values of where it believes the shards are currently located. So as we see, when a client makes a request on a key, that involves potentially contacting multiple servers to fulfill the request. However, the Grove Key Value Server client library hides all of that internal messaging, giving an API with simple key manipulation operations that are no different from, say, an in-memory hash table. In particular, we call the piece of code that on a client handles this problem of contacting servers to carry out a request a clerk. So here's a signature for the struct corresponding to a clerk. Internally, it consists of clerks that handle talking to the coordinator and the shards. And then we see the API operations for manipulating keys. So we have put and get here, and they're parameterized by a clerk struct that we're going to operate on. These put and get look not any different than you'd expect for a hash table, say. Let's take a look at the clerk code implementing get on a client. What the clerk does is, repeatedly in a loop, it looks up what server it expects has the key based on its cached mapping of shards to servers. Then it contacts that corresponding server and issues it a get request. If the server responds back saying it doesn't have the shard containing that key, then the clerk contacts the coordinator and asks it to send an updated shard mapping, and then retries again. On the other hand, if the shard responds with the value of the key, then the clerk exits the loop and returns that. So the key here is we're looking for a specification in which clients can think of get as just behaving like a normal lookup in an internal hash table on that node, without having to consider this messaging that goes on between the multiple nodes that are potentially involved in a lookup. Our client-side library for our key value service supports multi-get, that is, issuing GET requests in parallel. Here we see a specialized case of just get2, which does 2 gets in parallel. The way this works is it creates Go threads that each separately perform a get and then joins their results and returns those. This kind of within-node concurrency and parallel lookups is important for performance in certain use cases. And so we'd like to be able to reason about this kind of client-side concurrency. Similarly, the server-side implementation also has plenty of instances of multi-threaded concurrency within each shard server. The last complexity we want to tackle here is that our key value service client does not directly issue network requests to servers. Rather, it uses a library for remote procedure calls that we've implemented. Although our library for remote procedure calls is simplified in some ways, it does capture a realistic pattern of programming that's used in many implementations, where a library provides an abstraction to clients of behaving as if they're just making a call that executes on another server and returns the results. So clients can assemble a struct containing the arguments for some function they're trying to call, and then they call something which then is dispatched on a remote server that collects the values and sends it back to the client. So one challenge we have to address is how do we verify the behavior of remote procedure calls over an unreliable network primitive? Now that we've seen the challenges that Grove is trying to address, let me describe how the framework works. So as I mentioned, Grove is based on the ideas of concurrent separation logic. So I'll first give some background on how separation logic works. Separation logic adds a new connective to Hoare logic called separating conjunction, which we write as this asterisk or star. The assertion P star Q can be read as a kind of conjunction, meaning that both P and Q are true. However, it's stronger in some sense than normal conjunction, that it additionally means that the program state can be split into two disjoint pieces which satisfy P and Q respectively. What this means is that the resulting logic we obtain is substructural. In particular, when we have an assertion P, it does not entail P star P, in contrast to normal conjunction where P entails P and P. Additionally, separation logic introduces a heap points to assertion, which we write as X arrow V, and that means that a location X in memory stores the value V. Because of the interpretation of the star or separating conjunction as meaning disjoint pieces, when we have an assertion like X points to V1, star Y points to V2, we immediately know that X and Y cannot alias because, by the definition of the separating conjunction, it must be possible to split the state into two pieces, one satisfying and containing X, and the other containing Y. This points to assertion is used when we do operations that manipulate pointers. For example, if we dereference a pointer and we know that in the precondition X pointed to V, then in the postcondition we know that it must return that value V, and of course afterwards X still points to V. Concurrent separation logic observes that this idea of separation allows us to reason about threads in a concurrent system in a modular and thread local way. So in particular, if we're reasoning about the parallel execution of two threads E1 and E2, which I'll write as E1 vertical bars E2, then this inference rule says that if you want to prove a triple about that parallel execution, where in the precondition you show the state can be split into two disjoint pieces, one satisfying P1 and the other satisfying P2, and then you can prove separately a triple about E1, where in the precondition has access to P1, and then a triple about E2, where in the precondition it has access to P2, then we can deduce that a triple about the parallel composition, where in the postcondition we get the postconditions of the two separate threads joined together with the star. The idea here is that if P1 and P2 are disjoint pieces of state, then E1 and E2's parallel execution can't interfere because we know E1 only needs the stuff in P1 and E2 only needs the stuff in P2. Of course, we want to reason about scenarios in which the two threads don't just access entirely disjoint pieces of state for their entire execution. That is, we also want to handle scenarios where threads must share resources. To handle this, concurrent separation logic has what's called an invariant assertion, which we write as some assertion P with a box around it. So this invariant assertion P means that P will hold before and after each step of execution. And the key fact is that invariant assertions are what we call duplicable. That means that if we have box P, that entails box P star box P. That means that we can duplicate P and send it to both threads in the parallel composition rule that we just saw. Now, how do we use an assertion that has been placed inside of this box and is known to be an invariant? Well, the key is whenever we're trying to prove a triple about an expression E, which is atomic in the sense that it reduces to a value in a single step, then if in the precondition we know R is an invariant and we also have P, then we can open up the invariant and get access directly to R in our precondition. However, what we're required to do is show that in the postcondition the invariant R is reestablished. And then we have to put back R into the box, and so in our normal postcondition below the line, we just get Q with R removed. So this is why this rule corresponds to the idea of the invariant showing before and after each step of execution. We got to assume it in the precondition of E, but we immediately had to reestablish it after E took a step. Now, concurrent separation logic has been enormously successful in reasoning about multi-threaded code that runs on a single machine. How does Grove take that and make it also sound for reasoning about distributed executions with multiple nodes, each of which may still have multi-threaded computations? Well, the key idea is that we index our Hoare triple by a heap ID H, which indicates in some sense which machine the Hoare triple is talking about. Similarly, we subscript and index our points to assertions with a heap ID H, which indicates on which memory we're referring to when we say that some location stores a value. So we recover, for example, the rule we saw earlier about dereferencing a pointer, where if our Hoare triple is subscripted by heap ID H, meaning we're running on a node that has this heap H, and we have a points to fact that's describing that memory for that same machine with heap ID H, then we get the rule we saw before. Now, the key thing that's going on here is that generally speaking, we can do proofs generically with respect to H. That is, we can quantify over the H that we're considering and prove once and for all that the rule holds. And that's because most of the time when we're reasoning about distributed code, we don't need to make reference to the contents of in-memory state of other nodes. Okay, so it's rarely the case that some Hoare triple would need to make reference to some particular heap ID H and some other distinct heap ID. So by proving our triples generically once and for all for an arbitrary heap H, we recover most of the standard rules of separation logic. Next, we introduce a kind of points to assertion for describing the channels that nodes use to communicate with each other. So we write C and then a points to subscripted by chan and then a set M of messages to mean that M is the entire set of messages that has ever been sent across the channel C. Okay, so the rule for sending takes as a precondition this points to fact where the set is M, and in the postcondition we get back the points to, but with that new message added to the set. And receive, what it does is if M is the set of messages we know to have been sent in the precondition, then in the postcondition we get that some M from that set has been returned. Alright, so this set of rules in this specification captures the fact that our network is unreliable in the sense that messages can be dropped and duplicated. The receiver may never see some message M that's in the set, and it also may see some M multiple times because each time it can get the same message from the set. The distributed soundness theorem for Grove tells us that if we want to verify a distributed system with nodes running programs E1 through En, then what we can do is prove a separate triple about the program running on each node. So we prove a triple about E1 running on heap ID H1, and so on all the way up through En. And then what we have to do is show that the preconditions for those various triples are derivable when we take the separating conjunction of all of them, using just the initial configuration of channels that the nodes communicate over. Okay, and what we're guaranteed is if that we're able to prove such a collection of triples, then the collective system never triggers a fault. That is, the nodes never get stuck in the sense of triggering undefined behavior or violating one of the local invariants that we set up using an invariant assertion. Now, in some ways, the structure of this rule is very similar to the parallel fork composition rule we saw for reasoning about forking and concurrent separation logic, where we had the same idea of when we want to reason about multiple threads, what we have to do is split up the initial state into separating conjunction joined pieces, and then we give each of those pieces to each of the threads in their precondition. And indeed, the soundness proof here has a lot in common with the way that that rule is shown to be sound in classical separation logic. Let's turn our attention now to specifying and verifying libraries for remote procedure calls. So the remote procedure call library that we've implemented is called URPC, the U standing for unreliable. So using the network API that I showed a few slides ago, this library implements remote procedure calls. So servers can register some function F, which they are willing to run on behalf of clients. And then a client that's in communication with the server can call that function F and pass it some arguments. Now, because our network is unreliable, F may run multiple times due to the messages requesting that the RPC be invoked being dropped or duplicated, or being resent by the client if it's worried that the message has been dropped. Now, how do we come up with a specification for a function F being offered as a remote procedure call? Suppose we've proved some triple about that function F, like this precondition P and postcondition Q. What spec then should we be able to give on the client side the act of calling the remote procedure call? Now, there are two things right off the bat that we can tell this specification must obey. First of all, we shouldn't refer to either the local state of the client or the server when talking about the precondition on the other. So we do that, of course, we can enforce that by ensuring that the preconditions we use have no dependencies upon the local heap ID subscript H that we saw we can annotate with triples. The other complexity is that we need to allow for F to run multiple times because the network is unreliable and duplicated messages or resent messages may trigger repeated invocations of F. The solution is that we require the precondition P to be duplicable in the sense that P should imply P star P. This captures the idea that F must be able to be invoked multiple times because this means that once we show the precondition P holds once, we can show that it keeps holding in the event that F happens to get reinvoked. And so long as we have this property, the client-side triple about the RPC call will have the same pre- and post-condition P and Q as we derived on the server side. Now, on top of this unreliable RPC mechanism, we'd like to achieve exactly once semantics. in which an RPC call invokes a function only once on the server side. To do so, we'll use a standard implementation strategy called a reply table. So the idea here is that clients have unique IDs, and they number their requests with sequentially unique sequence numbers. Then servers keep a cache of their most recent response to each client, along with the sequence ID for that request. Now, when a server gets a request, it checks to see if that request is already in the cache table, and if so, sends the response it previously sent in response to that request. Otherwise, if it doesn't find it in the table, this is a new request, and the server runs the function and sends the result and caches that response. Now, what's key here is that servers only have to remember the one most recent response they've sent to a client. If a message much older than that most recent one is received, the server can safely ignore that message because from the very fact that it's responded to subsequent IDs, it knows that the client at some point saw that earlier response to those earlier requests. So more concretely, let's look at our implementation of reply tables for the put RPC on the server side. So this is a simplified version which doesn't have the error handling for the scenario where the key isn't on the server. So what the server does is it stores for each client ID what is the most recent put that it's responded to. Okay, so on line 3, it first checks in that table, it looks up the value for the particular ID associated with this request, and it sees whether that sequence number is greater than or equal to the sequence number of this incoming request. If so, it doesn't do anything because it knows that it's already processed this put. Okay. Otherwise, it goes ahead on line 4 and through 7 and actually updates the value of the key in its stored table. And additionally, it updates that the last responded to sequence for this client ID is the current request sequence number. Now, this is a special case here where the caching that the server has to do is simplified because a put, we only just acknowledge that the put was performed. We don't actually have to return any value. So the caching that goes on in this reply table is just the sequence number of the most recently processed request. And then on the client side, it's very straightforward. We annotate our put request with the sequence number. We have a running counter that we increment each time we make a put call. And then what happens is that we use the URPC interface to repeatedly call that put function in a loop until we get an acknowledgement. Now, how do we derive a specification for this exactly once semantics implemented on top of URPC? As we saw, the URPC specification requires that the precondition of the function being invoked be duplicable. But the exactly once semantics, of course, should not require this in the sense of what's exposed to the user, because the whole point is that the function will only be invoked at most once. Each request has a sequentially increasing ID number. So what we do is we associate that ID with a piece of ghost state in the proof. And this is some state that's not actually physically represented in the system, but is just used as a proof reasoning technique, a common trick used in reasoning about concurrent systems and separation logic. Then what happens is the client creates what we call an escrow invariant. So this is an invariant of the form P or that ghost token talk, where P is the proper precondition of the function. Now the key is that an invariant assertion, as we saw, is duplicable. So an invariant assertion like this can be used as the precondition for URPC. What happens is that when the server gets an incoming request with this kind of precondition, it can use that ghost state token that it owns to kind of trade and take P out of the invariant using the invariant opening rule we saw earlier on. A similar process is used in the reverse for the server to send back the postcondition Q of the RPC to the client. Using this technique, we get a specification that allows the precondition P to be arbitrary. Using these techniques for exactly once RPC semantics, we obtain a specification for our key value service that meets the goals described in the beginning of the talk. In particular, the specification introduces a points to assertion for talking about the contents of keys. So we write K maps to V to mean that key K stores the value V. If we've established a key value clerk for communicating with the key value service, then if we know, for example, that the key points to W and we do a put storing the value V, then in the post condition we get that K points to V. Similarly, if we do a get and we knew in the precondition that K pointed to V, then the post condition tells us that the return value is V. The get2 implementation, that parallel multi-get we saw, obtains the following specification, in which if in the precondition we own both of the keys that are being read, then the postcondition says the return value is the tuple corresponding to each of their values. Now the key here is that those specifications resemble exactly what we'd expect for an in-memory hash table. To test how well these specifications work, we implemented on top of it two client services. First, a lock service that enables us to lock values atomically using keys to store the status of the lock, and a simple bank that allows us to do atomic transfers between the contents of bank accounts. Because the specifications for the key value service operations are just like an in-memory hash table, the proof of the bank, for example, is as if we were using a local hash table and locks and doing the proof in standard separation logic. This table shows the relative lines of code and lines of proof used in various parts of the implementation. We have about 100 or so lines of trusted library code implementing our networking layer, and about 1,000 lines of implementation for the key value service and the clients on top. The proof to code ratio is quite substantial in some respects, but one should keep in mind that this is implemented in Coq, which has very minimal automation support. Since Grove touches on aspects of implementations that affect performance, I want to discuss our experiments evaluating the scalability of our key value service. In particular, we're interested in scalability in two senses: multi-core scalability, as we increase the number of cores on a shard server, and multi-node scalability, as we increase the number of shard servers. The first experiment evaluates multi-core scalability, where we have a single shard server and give it an increasing number of cores. While we fall short of perfect linear scaling, we do see that the performance and throughput increases as we scale up the number of cores, leveling off around 9 or 10 cores. Second, our experiment here evaluates multi-node scalability, where what we do is we start with a single shard server and then every 30 seconds or so add another shard server and trigger rebalancing, which is indicated by kind of the spikes up in throughput as another server is added. So you see when a server is added, temporarily the throughput dips, and that's because the other shard servers are busy sending their keys to that new server that's coming online. As we've seen, Grove adapts techniques from concurrent separation logic to distributed systems. In future work, we'd like to address issues of fault tolerance and replication. In particular, we're interested in using our perennial program logic that we've developed for reasoning about single node concurrent crashes and recovery reasoning to be able to handle nodes failing and coming back online as part of sophisticated protocols for replication.
Thank you very much, Joseph.
Thanks.
So, yeah, very, very interesting. Let's start taking questions.
I guess, would you provide any background on how this compares to other systems like Verity or that have done apparently a similar approach of proving things in Coq and translate it to a verified implementation?
Yeah, so Verity, for example, uses Coq extraction. So the implementation is also written in Coq, and then one uses a kind of translation from Coq to OCaml. Whereas here we sort of write the code in Go and then can import it into cock to reason about it. I think that gives us some advantage in terms of we can make better use of multi-threaded concurrency, because by default, the cock code that's extracted to OCaml is single-threaded. I think in Verity, they try to do clever things like running multiple processes, but then you wouldn't be able to take advantage of some of the sharing of, say, the cached lookup table for where shards live.
Okay, thanks.
Yep.
So is the importing the cock code into cock, is that automatic?
Yeah, that's automatic. We had earlier written a tool for doing that for reasoning about file system implementations that we've done for that perennial project, and we're able to reuse the same infrastructure for this tool.
Great. So I have a question. So I'd like to understand what the use of separation logic saves me compared to if I wanted to do this proof with a more traditional global invariance, basically, like I would do in TLA, for example, or IV.
So the main advantage is that, for example, if you think something about like the shard server, the invariants here are local. So a given shard server, when we think about proving its correctness, we don't have to talk about any of the other shard servers in the system. The shard server really only has to know about the keys that it owns or it's currently managing, and it needs to know how to communicate with the coordination manager. But as far as it's concerned, there could be an arbitrary number of other shards in the system. The other benefit, which we haven't necessarily explored in this example, is, for example, the shard server verification is independent of how we actually verify, say, what the coordination manager does. So one thing that we're looking to do in future work is, for instance, swap out the implementation of the coordination manager and make it replicated, for example. As long as the Hoare triples it exposes stay the same, the shard server verification wouldn't have to change.
Yeah, makes sense. Thank you. Yeah, I think in the proofs I've done personally using global invariance, I was basically just relying on the solver to just figure out that my invariant was trivially preserved by, let's say, transitions of another server because they use different variables or something like that. But I can see how this might break down in more complex cases.
Yeah, I mean, concretely, I don't have like a definitive thing where it breaks down, and it's sort of balance of how good is your automation, you know, and maybe it does scale up for things, but yeah.
Any other questions? So maybe another, oh, Sven, do you want to ask a question? Maybe another question for me. So I was wondering if you also prove the soundness of your framework in Coq, or?
Yes, that's right. The framework is proof sound in Coq, and it leverages the sort of existing soundness proof for the single node concurrency framework that we're building on top of.
Great, very impressive.
Thanks.
Okay, well, if there are no other questions, we're going now to take a 10-minute break before the next talk. So let's say we'll reconvene at do time zone calculations 5:55 p.m. Okay, thank you very much.
Hello.
Hey, Christopher, are you there?
Can you hear me?
Yes, great. Would you like to try sharing your screen or playing your video if you have a recorded talk?
Yes, I will try to share my screen. Just 1 second.
Oh, I need to make you a co-host. Okay, now you should be able to share your screen.
Test, test.
Yep.
Oh, sorry. I just saw the messages. They don't. Zoom on Linux, it doesn't show up unless I click some other bar. Should I go ahead?
Oh, we're starting at 55. So
Oh,
4
okay.
minutes.
I get it.
We're running a little late.
Okay, so let's reconvene. Welcome to the second session of FRIDA today. And we have two more talks. The first one is by Christopher Gers, and it's about zero knowledge proofs and how to prove formally their correctness. Christopher, go ahead.
Thank you. So I must admit at the outset that this is more of a talk about a lot of interesting questions without solutions than it is a talk about solutions to questions. I work on the practical side of things, and we are trying to employ zero knowledge protocols in lots of distributed systems where we want to be able to reason formally about privacy, about incentive compatibility, about correctness, about safety, about soundness, about a lot of properties. My central thesis here is going to be that, well, I guess a few parts. One, that zero knowledge protocols are very useful in distributed systems in ways that perhaps we haven't thought so much about yet, in like non-obvious ways. Two, that they are not like very well formalized at all, and that formalization of them is critical because of, in particular, the machinery of how some of the zero knowledge protocols work, how you have to write circuits is very particular, or even if the logic which you're implementing is simple, so even if like in some sense the protocol is simple, the mechanism itself is very complicated and it's easy to get the protocol right, but screw up the mechanism. And in some sense, from the perspective of practical security, it doesn't matter if you get the protocol right, if you screw up the mechanism. A good example of this is like an unsound proof system, and that was used by the original version of Zcash, so practical deployment of zero knowledge proofs. So three is that we need better tools for reasoning about the distributed systems, which include zero knowledge protocols formally. And then I'll talk a little bit about one of our approaches in constructing a tool called JUVIX, which is a dependently typed language conducive to formal verification, which can compile two zero knowledge circuits. So which can be used to reason about protocols, which include zero knowledge components. I'll talk a little bit about that, which is a work in progress, but also just focus on the kind of areas of the design space here, which I think merit further exploration. So specifically, also, I'll start off with a little introduction to zero knowledge proofs, as I realize they're, have some intersection, but not complete intersection with the distributed systems community. I'll talk about some cases of where I think we should be thinking about zero knowledge proofs in distributed systems and where they solve particular problems. I'm going to give a specific example of dealing with front running, which is a kind of, I suspect that the kinds of problems I present in this talk are going to be a little bit different to the kinds of like properties I'm interested in verifying are a little bit different to the kinds of like traditional distributed systems properties. It's not just safety or something like that, and the actors are not just Byzantine or honest. We have more nuanced or more like game theoretic assumptions, which we have because we need to have them in practice. We don't have them because they're more fun. I think they're less fun. It would be great if we could reason with simpler assumptions, but we don't always have that option. So I'm going to talk about a specific case of preventing front running, which is something that happens in practice on blockchains, so in applied distributed systems, and where zero knowledge proofs come in useful there, and also where we need almost a kind of information theoretic sort of formal reasoning, which I think we might want to move towards, although I'm not yet totally sure how. Then I'll talk about the tool I mentioned, JUVIX, which we work on at Helix and Anoma, which is a dependently typed language in which proofs can be written that also compiles to both regular executable code like LLVM, IR, or WebAssembly that can be used to implement distributed systems, and it compiles directly to zero knowledge circuits. And the way in which it supports this compilation is conducive to formal verification of protocols which include zero knowledge proofs. So I'll sort of talk about why, and I'll talk about why we've taken this approach. I'll briefly outline how JUVIX works and what sort of reason I have for thinking that a dependently typed language might possibly be efficient enough to compile to code that could actually be executed, since that's a hypothesis that you might be justly skeptical of. And I will talk about some future research directions which we're pursuing and which I think merit exploration. So first, boy, I actually can't, I don't know, maybe this, well, not enough cameras anyways. I was going to ask how many people have are familiar with zero knowledge proofs, but I'll just quickly walk through this. Zero knowledge proofs are like a mathematical abstraction, so there can be different ways of implementing them. A common way of implementing them is via a polynomial commitment scheme. So, for example, Halo 2 and Plonk and different kinds of zero knowledge proof systems, which have been recently developed and are quite efficient, more efficient in practice, rely on polynomial commitment schemes. But the abstraction itself is just any internal implementation which allows for verification of the properties of some information without conveying anything about the contents other than the properties which are being verified. So in zero knowledge proofs, there is a prover who knows something, and they wish to convince the verifier about some property of the something which they know. This all sounds very abstract, that's because it is. So for example, the prover might know the preimage of a hash. And the prover wants to convince the verifier that it knows a preimage, a plaintext that hashes to some particular output without the verifier learning anything about the plaintext which the prover knows other than that it hashes to that particular output. You may have heard a example of an interactive zero knowledge proofs involving graph coloring and hats, which I won't go through here, but the sort of very fundamental mathematical constructions are interactive, but we can turn them into non-interactive zero knowledge proofs, which then can be verified, like a prover can basically create a transcript of the interactive protocol, and the verifier can verify that asynchronously. So this is useful for many cases in distributed systems where, unless we absolutely need to, we don't want to create extra interactive protocols, say on a distributed ledger where we want to do post proofs along with state transitions, and the proofs attest to something related to the validity of the state transitions. So the verifier in that case is are the nodes who are verifying this replicated state machine, and the prover is the person submitting the transaction. So they're not engaged in any sort of interactive negotiation. So the non-interactive transform is necessary for most distributed systems use cases. Zero knowledge proofs have three properties which are critical in reasoning about their usage. One, completeness. We want the verifier only to be convinced by the prover if in fact the statement, we want the verifier to be convinced by the prover if the statement the prover is proving is in fact true. So if I know the preimage of a hash function and I follow whatever the zero knowledge proof system is to create a proof that I know the preimage of this output, then I should be able to convince the verifier. If I do not, in fact, know a preimage which hashes that output, then I should not be able to convince the verifier, except in some very unlikely case that we can assume won't happen. That's soundness. And then zero knowledge is that I do not learn anything else. Of course, I learned something. I learned the thing which is being proved, except with negligible probability. I learned that the prover knows something which hashes to this value, but I don't learn anything else. So this can be used for both privacy and computational compression, basically by hiding the inputs and outputs, affecting some state transition and proving that the state transition was valid. So in the case, let's say, an easy way to get privacy in something like an unspent transaction output system. So an unspent transaction output system is where you represent some kind of asset by assigning notes which have a balance to users. So if I send you five Chris assets, you get a new note or a record basically, which says that you have 5 Chris assets, and then you can spend that record consuming it to send it to somebody else. So you can think of it like a kind like cash, like you have different denominations of bills in your wallet, and you combine, 2 20s and a 10 together, and that makes a 50, right? So a unspent transaction output system is just a digital way of implementing that. And you can easily achieve privacy for an unspent transaction output system by using a zero knowledge proof to prove that you know notes with the relevant properties and that you're creating notes which match. So in something like Bitcoin, I would spend my 220 BTC outputs. They're called in Bitcoin, but no, it's the same thing. My 220 BTC outputs and my 110 BTC output, and create 150 BTC input, which I then assign to somebody else to whom I'm sending the coins, or it could be myself if I just want to recombine them. In a system which uses zero knowledge proofs like Zcash, instead of doing all of that in public, I create a proof that I know these 3 notes, so that I know a note with 20, another note with 20, and another note with 10, and I create one note with 50, and then I use some special tricks to prove that the net sum of inputs and outputs is 0, so that I'm not creating or destroying quotes. And because I'm using a zero-knowledge proof to hide the nodes which I'm consuming and the nodes which I'm creating, along with the recipient, the person observing the ledger, that's the verifier, or anyone observing it, doesn't learn anything about the contents of the transaction. So they're providing privacy, and they can easily provide computation for which you generally don't need a zero-knowledge property, computational compression, just by having some like input and output, and the zero-knowledge proof is proof of validity of the state transition, where the circuit encodes whatever the state transition validity conditions are. So how might zero-knowledge proofs be useful in distributed systems? There's sort of, I should have included a inverse exponential curve here. Zero-knowledge proofs are getting rapidly cheaper in terms of computation and storage, to the point where at the moment they're mostly used in cases where privacy is really critical and we're willing to pay high costs for, and we have very simple circuits, so we're willing to pay high costs for compute, and we don't mind so much if we have to store a bunch of proofs, but they're also going to become useful in cases rather soon where we're just like tossing the proofs away, where we're just using this to avoid bandwidth or avoid a bunch of computation. So in the case of consensus algorithms, zero-knowledge proofs we think may be useful in proving that you have, basically that you're following the protocol. So that, let's say you've received certain past messages without actually, like, you don't want to send the messages because that would turn your, I don't know, a linear or quadratic gossip costs into cubic costs, because you need to send all of the messages you've received all of the other validators to prove that you're following the protocol. But you can instead create a zero-knowledge proof that you've received such messages, and the proof size is constant. I forgot to mention the zero-knowledge proofs we're interested here are succinct. So, you know, even if there are like 100 messages and you want to prove you've got 100 votes before you move to the next round, let's say in some kind of consensus algorithm, you could just construct a zero-knowledge proof, which would prove that you know of such votes, that they correspond to like actual people who are eligible to vote. And then you could send that compact proof, 500 bytes or something, along with your messages in consensus, right? So it can, because it's succinct, that can reduce by an order of magnitude message complexities, where message complexities are dependent on sending around, like somehow sending around proofs that you have received certain messages from other people, which is very common. Zero-knowledge proofs in distributed systems. So I mentioned the case of Zcash, but the case I'm going to talk about next here is another case where I think we want to be able to do some kind of verification about possession of information itself, and this is in dealing with front-running. And then we think zero-knowledge proofs would also be useful in gossip networks. So in the context of the project we're working on, we're building a gossip network where users gossip around pieces of data, some of which are basically intentions to partial intentions to execute a particular state transition. So I might say, this could be for trading concretely. So I might say that I have some eggs and I want to trade it for some toast. And I create some kind of intent. Some other person creates an intent that they have toast and want to trade for eggs. Those get gossiped around, and they can be combined eventually into a transaction. In a lot of those messages, we need, in order to safely, in an incentive-compatible way, gossip them around, the nodes which are gossiping need to do some validity checks, because otherwise they would be subject to denial of service, because we have to make it computationally cheap to perform this gossip. So we can use zero-knowledge proofs in this case to prove some kind of validity relative to the ledger, so relative to the state of the distributed system. And that proof must be sent alongside the message, and the node just rejects it if it doesn't have it. Right, so there's a case where we're not ever submitting those proofs to the ledger. We're not storing them anywhere long term. They're just used for transient gossip. So a more concrete problem of front running. Here I'm talking about a replicated ledger. So some kind of, this could be using Tendermint or some kind of EAT consensus, where there is a particular entity, so one of the validators or one of the nodes in the network responsible for proposing a candidate block of transactions. So proposing the next set of transactions and the order in which they should be executed. That proposal then gets voted on, and if 2/3 of the voting entities, validators, or it could be just like a permission system, so it could be a specific set of people as well, but some specific agent is responsible for ordering transactions into a block. And they have relatives, these transactions prior to being ordered in a block are gossiped around. So they're sort of sent around this gossip network. A proposer chooses which to include, they order them, they include them in the block is then voted on. This creates a game theoretic asymmetry because these transactions, if they're public, include information about state transactions which might be executed, but whose execution depends on the state of the chain or the state of the ledger at the time when those transactions are actually like included in the order, or so to speak. So usually in something like Bitcoin, we view the miners collectively as determining the ordering of transactions. So that's true. But here there's also a case where the proposers, the single entity within the single entity is choosing the order of transactions in a block. And that gives them an advantage because they can say, oh, like someone's going to place a market buy order for this particular asset. I'm going to sandwich it. I'm going to put my buy in right before they do, then they'll buy at a higher price than I can sell back to them, right? So that's a kind of game theoretic advantage that we do not want the proposers of particular blocks to have. And the solution we've come up with in our case is to encrypt transactions before they are ordered. So in the gossip network, we're gossiping around transactions which are encrypted to a threshold public key shared amongst the nodes operating as distributed system. The proposer must include in their block encrypted transactions to which they commit to an ordering. Then once those transactions are confirmed and that ordering is set, they're decrypted, executed, which solves this unfair game theoretic advantage in the sense that the proposer no longer knows anything about the transactions that are included. So they can't strategically position their own transactions or reorder them to try and gain an advantage relative to the users who didn't know what other transactions would be included alongside theirs. But it creates a new problem.
So just one question, please.
Yeah, go ahead.
So here there's also, like even if I'm not a proposer, I can try to front run transactions by just sending mine with higher gas costs associated, so that people will pick mine, the proposer will pick mine instead of others. Is that the same problem?
You mean even if transactions are encrypted, you can choose to pay higher like fees? Or?
I guess if they're encrypted, then I can't, right? That would solve the problem too.
I see. So it is true that independent of whether the proposer is doing front running, anyone could do front running just by paying more. Yeah. Right. But that's kind of I mean, because the proposer is choosing to like order transactions which have higher fees first, it's kind of a subset of the same problem, I think. Right. Okay. But your question belies my next point, which is that it seems that we've solved the problem, but we actually have to go back a step because there's something else that we need to consider, which is that in choosing transactions to put in a block, a proposer needs to fulfill another condition, which is not to put too much execution in the block. This is specifically a problem for systems which do complex things. So if you have like one kind of transaction and it sends assets or it does something very simple, you don't have this problem. But more complex systems do. In a system like Ethereum, the execution on a replicated ledger is metered by gas. So you pay a certain amount of gas for each instruction, and you must allocate a specific amount of gas to your transaction and demonstrate, because the transaction itself isn't executed until it's like confirmed and ordered on the ledger, because like executing is expensive. You don't want to execute it until the fee has been paid. But it needs to be possible to very quickly check that the fee can be paid, because otherwise you don't want to put the transaction at the block in the first place. So when we're encrypting transactions, because then anyone could submit transactions without paying fees. It's like a DOS vector. So even when transactions are encrypted, we can't encrypt the fees, because if we encrypt the fees, then I can not have any money and just keep submitting encrypted transactions for which I'm paying 0 fees and cause a lot of wasted space and computation. So we need to put part of the transaction outside the encrypted component, and that must include a fee, and it must include a gas limit, because if the proposer doesn't know the maximum gas a transaction will consume when it is actually executed, then they might choose to include 100 transactions and they all take like almost the whole block's worth of execution, assuming that we don't want our system to fall behind and there's some throughput limit on how fast we can execute transactions. So that means that we need to put this gas limit in the transaction outside of the encrypted component. But of course, that's a privacy leak because the amount of gas that you allocate to your transaction conveys some information about what the contents are, even if it's a limit. Now we can make it more coarse, then it's less of a privacy leak, but it's still like a violation of the otherwise, otherwise in a sense, perfect privacy that we're getting here. So here we think zero-knowledge proofs can come into play to prove that you can prove that you have, well, we need to do a little bit of homomorphic addition too, but to prove that you have the ability to pay a fee without revealing the exact gas cost, without revealing the gas cost and without revealing like the account which is paying the fee, which also is a privacy leak. And that will get checked by the, that will be still outside of the encrypted component, but it is a zero-knowledge proof. So all it conveys is that someone is paying for the transaction and they have enough tokens or whatever is being used to pay for gas. They have enough tokens to cover the fee, like the fee per gas unit times the gas limit of the transaction itself. And then we can do something like similar to Zcash, and we can homomorphically add all the gas limits together. And we can check that they're not too high. Okay, so I'm going to jump here a little bit and talk about one of the, so I guess, let me put it this way, that here, what we have what probably looks like a very messy problem. We have some distributed system, which has properties that we know pretty well, like BFT consensus. We have a replicated ledger on top of that. We have transactions within the ledger which do things which we want to reason about game theoretically. Like we don't want them to be front runs. There's some kind of value being transferred, or there's some sense in which the participants in the system have agency and they have goals, and we don't want it to be unfair. That's what I mean when I'm talking about game theory. And then we need to deal with the fact that we're operating in an open system, so we need to prevent denial of service, which means we have stuff like gas. So here's a case where we have this like complex gestalt system, and we have components which are well verified, like say the BFT consensus algorithm and the maybe the zero-knowledge proof system itself, but the whole system welds these together in a way that we're just hand-waving. So there's no particular, we want to be able to talk about properties of the Gestalt system like fairness, but we can only talk about that right now in a English language sense. We don't have a formalization. Part of the difficulty in formalizing in a sense that is practically useful work like this is that we also need to update the system and change it over time. And we do not want, we want it to be in some sense integrated into the tool chain. Or if we have, we can write a spec or something like that or reason about it, but then there's always the possibility that the code we write will diverge from the protocol which we've designed and verified. So for that reason, we've decided to pursue the approach of trying to create a language in which it's possible to reason about the properties of these protocols, which we're implementing, where that language can also compile to code that we can execute. So kind of, you could think of it like an executable spec, but of course we're taking a lot of inspiration from prior work and not reinventing the wheel, except where we absolutely need to. So that brings me to this particular tool, which we call Juvix, which is a dependently typed language for executable code. That's the most compact summary I've come up with of describing like the niche that we're trying to fill here. There are dependently typed languages which serve the role of proof assistants. I'm sure many of you are familiar with them, and they are fantastic. Juvix is not competing with them. Rather, Juvix is trying to create a language with similar proof verification capabilities, but that you can also compile to code that you can execute. And the reason for this is that we want to remove the gap between specification and implementation, because in practice, many bugs or issues arise not due to insufficiently well understood or verified protocols, although that certainly happens, but due to discrepancies between the protocols and implementation, especially when the protocols are changing rapidly. So there are sort of a few approaches to formal verification that you can take. One is to verify at the virtual machine level. So in replicated ledgers, there's often a virtual machine which contracts or which code is being compiled to. And this is also equivalent to, like, if you verify the machine code of, and it sounds kind of ridiculous when I say it, but if you think about code which is running on a replicated ledger and verifying the semantics of the machine code, the like VM on the ledger, that's equivalent to if you verified Paxos by writing a formalized VM for the x86 assembly code of someone's Paxos implementation, and trying to verify like safety properties of Paxos as a some sequence transition invariant of the x86 machine code. Now that sounds ridiculous, but at the moment that does happen at the VM level with blockchains. I guess I don't need to convince you that that's ridiculous. All right, verification in the language itself. Here's where, before we worked on Juvix, we tried to work with existing dependently typed languages such as interest and write backends for them, but we found out that they were too inefficient, so we decided to build a language from scratch. The key problem in doing this is in producing code that is efficient enough that you can use it in situations where execution is expensive, so like a replicated ledger, or where you need very high efficiency, like a circuit, which I'll talk about in a bit, while also having this high-level language in which you can write proofs and reason formally about the properties of the protocols which you're implementing. So Juvix particularly brings something called quantitative type theory, which provides a very granular kind of linearity. So if you ever used a language like Rust, you'll be familiar with linearity, but Juvix generalizes this using some research out of Strathclyde to sort of any number of usages. So you have like linear variables in Rust that you can use once, something like that. Juvix does that, but instead of using it once, you can also use it twice or 3 times or 4 times or any number of times. And however many times you use it, that can be checked statically. And we can use that information in the compiler pipeline to avoid a bunch of dynamic memory allocation and garbage collection in the output code. And specifically because we have this detailed usage accounting, all proofs, so all of the, we can write in Juvix proofs of the properties of the protocols that we're implementing, and we can erase those proofs so they don't translate to any runtime cost. We're just checking at compile time that say we can write something like proof of funds balance so that currency is neither created nor destroyed when you're sending a transaction, maybe even in private. And we can like pass that proof around. It looks in the language as if you had a proof that you were using as data, like in, say, especially Agda, if you use proof carrying data as a development pattern. But that gets erased at compile time. So if you have like a tuple where the second element, a dependent pair where the second element is proof about the value of the first element, then you can pass that around in Juvix, but it gets erased at compile time, so you don't pay any sort of runtime cost tracking it, which is very important for producing code that is efficient enough to execute. Let's get that. So Juvix also compiles to zero-knowledge circuits. And in that example I gave earlier, that was a case where we want to use ZK keys in the context of some protocol, which is also doing a lot of other things. They're just a component. But zero-knowledge proofs are, while very useful, are really, really bug-prone. Because of the mechanics of the proof systems we know at the moment, well, that's a fundamental limitation, but zero-knowledge proofs have to be written in circuits. So they have to be written in arithmetic circuits where you have input gates and the output gate is basically a Boolean, 0 or 1, does this verify. So for in the example, that means that you need to do things like implement hash functions in, and the circuit operates over field elements, but you need to implement hash functions in a circuit. And as you can imagine, this is tricky. And it's easy to have a correct protocol in some sense that you understand, or even that's verified as a protocol, but where you make a mistake constructing the circuit and don't check the right thing, because these circuits are written by hand. So in Juvix, we support a sort of multi-backend composition where users can write, in our system we call it a validity predicate, but users can write code that takes a public input and a private input and returns a Boolean, so just a function, and compile that to a zero-knowledge proof circuit. So for example, I could say that I could write a hash function and then define a function that takes pre-image the hash, takes that's the private input, takes the public input, which is the hash output, and returns whether or not like hash input equals output. Very simple. But Juvix will compile that to a circuit, which can then be executed with. But this, the split, Juvix can handle multi-backend compilation. So some of the protocol can be like, you can verify, you can reason about properties of the protocol in this dependently typed front-end language, but then different parts of the code can be compiled separately to circuits or to LLVM/WebAssembly, which you can execute, so that you kind of get this verification while also getting this separate implementation that you want for efficiency or privacy or whatever. And we think this is essential because if you just glue different parts of, if you look at a pretty complex protocol like this, if you glue different parts of code together, it's easy to make trivial mistakes. It's easy to make mistakes like you didn't serialize something safely when you're converting between a representation in field elements in a circuit and a representation just in some standard memory or structs in LVM code or WebAssembly code. And it's easy to make a subtle assumption about some property of underlying systems which you're relying on that's like just a little bit wrong, and then the Gestalt property which you think you have, you actually don't. So we think it's very important that users be able to verify the whole system, but because the whole system needs to use these different constituent components, our approach is to, that complexity has to go somewhere, right? That complexity can either be dealt with either time, every time when you're writing a bunch of components, then you can like reason about their interface boundaries and try and ensure that they're correct in your specific system. But we think that can be centralized, in some sense, logically centralized in a compiler, so that we can write once data conversions between a circuit, between field elements for circuit, and the kind of in-memory representation you would have an LVM or WebAssembly, and then assuming the compiler is correct, which is a big assumption, but assuming the compiler is correct, you can verify properties in Juvix at a high level, and you are reasonably well assured that your output code, which is being executed, will actually satisfy those properties. Right. Running up on time here. I know I was told to keep it to 30-35 minutes, so I will just say quickly, research directions. We're working on still lots of improvements to Juvix, the language, to make it more efficient in terms of output execution, mostly first-class usages where we can reason about functions where the usage of subsequent arguments depends on the value of prior arguments. And we're doing more research into, I really think for the like very practical context, we need the ability to model like actors with utility functions or actors with agency and specific preferences, and then formalize these kinds of hand-wavy fairness guarantees that we're trying to talk about in the case of front-running, for example. And we need to be able to reason about who has what information in the context of privacy and ensuring that we do not accidentally leak through various interactions like setting of gas limits. That one's pretty obvious, but sometimes it's not. Ensuring that we do not accidentally leak a data which we want to be private or metadata which we want to be private in our construction of these complicated protocols. That's it. Thank you very much, and I would love to take questions if there's time.
Okay, yes, thank you. So let's see, do we have questions from the audience?
Yeah, I have a question. So if I understood correctly, you can use the Juvix language to model protocol level properties. And so I was wondering whether when you have cryptography, so as we saw in the previous talks, are you able to work in a kind of symbolic models to then do the proofs, or do you deal with probabilities and complexity assumptions and so on?
So you can work in, when using Juvix to do something like write a zero-knowledge proof system, which we haven't done yet, to be clear, but you can create, like, say, abstract algebra primitives like groups, and then construct a system using them and reason about the properties of the system as a function of the properties of the primitives. I don't know if that answers your question. Reasoning about like computational soundness or something like that. Yeah, I mean, you can do that. Jubix doesn't include specific support, like it doesn't include built-in, I don't know, built-in assumptions, but you can use you know, anything which is expressible in like the logic you can reason about.
Yeah. Okay. Oh, well, yeah. I was thinking that sometimes, you know, when you want to prove security arguments involving cryptography and zero knowledge proofs, you have to prove that the probability of that your adversary is going to guess your secret is negligible, or things like that.
I see. Yes, you could prove that. I mean, that would be like if your adversary is, you need to prove something like your adversary has to execute this function, which is like a random guess, basically more than some number of times relative to the size of your input or something like that. Now you're still making an assumption. So as long as you have, say, a computational soundness property, you're still making an assumption about the computational resources your adversary has. You can reason about what that assumption is and like verify that what you think it is for your protocol is correct.
Right. And so is there like built-in support in the language to do that kind of reasoning, or do we have to model probability distributions using a monad or something like that?
Oh, I see. No, at the moment you have to model it using a monad, but that's a good idea. Or you could do it. I mean, we don't. It's not like a probability monad where you're executing things. In this case, it's just reasoning.
Right. I mean, you'd have to erase that, I guess.
Yeah.
When you're generating code. Yeah. Thanks.
Thank you. Was there another question, Dante? Or
So I haven't seen other questions. No, okay. So from the practical side, do you have experience with the language and the proofs? Have you verified larger applications with it?
Jivix is still like pretty early experimental stage. We're working on verifying some of the protocols we're working at Helix, specifically this front-end front-running protection that I mentioned, and we're working on verifying some circuits. So we're building a circuit for private bartering that we want to verify the protocol of, and that we want to verify. Eventually, we want to verify like the compilation pipeline in the language as well. I didn't mention this in the talk, but it's the next step, because obviously what we're doing here is centralizing the risk into the compiler. So instead of you know, checking all the correspondences between different parts of your protocols yourself, we're doing like data marshalling and stuff. We're relying on the compiler to do that, and we're relying on, you know, the type theory and everything to be correct, but also the actual transformations from, because we're creating code that could be executed. The actual transformations resulting in output code, you know, aren't verified at the moment. They're just, we, you know, reason about compiler correctness, and we've written them down as specified, but it's not formally verified. So we'll need to verify the compiler, all of the compiler transformation, like compsert or something. We need to verify the compiler transformations in the compiler, I think, before we have really, really high assurance.
Okay, so that's all in the future. Lots of work to do. Okay.
Yes. Yeah.
Cool. Interesting.
Maybe just another question.
Mm-hmm.
I was wondering if, so except for the fact that you need to erase proof to obviously to not incur runtime costs, is there something specific about efficiently compiling a dependently typed language compared to efficiently compiling, let's say, ML programs?
That has a fair amount to do with it. I mean, a lot of what, like many practical distributed systems right now are written in Rust because the memory management is very precise, and this helps with that. Part of it is just, frankly, writing a compiler which is designed to produce fast code. I mean, the Agda and Coq proof assistants are amazing, and you know, they dwarf Juvix in terms of proof assistant features, but they're not designed. They're not like very focused on producing fast code. So we do a bunch of transformations like continuation passing style and different sequences of inlining and stuff. So things like many things which say GHC or an ML compiler does do. I think the other thing that dependent types make more complicated is that you don't have, I mean, you have very precise guarantees, but they are at the type level in the language, as opposed to like you have to, your compiler needs to look at types of things to know properties which can use to perform specific optimizations or something like that.
So I guess would it be a practical approach to have a first pass that just erases all the proof aspects of the types, and then maybe, let's say I have an efficient compiler for OCaml, then maybe just translate what I have left after erasing the proofs to OCaml, and then use the OCaml compiler?
Yes, and that's not like, in some sense, that's what we're doing, but we do want to keep the information around. So we want to keep the usage information around, and we want to keep proofs. So we want to keep it around in the compiler. We don't want to produce code which manipulates the proofs at runtime, but we want the proofs available. For example, something like checked arithmetic, we can avoid doing safely if we have some proof that a variable is within bounds.
Right. Yeah, okay, makes sense.
Okay. Thank you again for the talk and a nice discussion. And let's get to the last talk today. I think, Giuliano, you need to make the co-host.
Yes. Okay.
Okay, can you try to share your slides?
All right, can you see my screen?
Yes, you see it. Okay, yeah. The next talk is by Bernhard Frage, and he's talking about the Sybil verifier.
Yeah, so thank you for the invitation. I'm talking about the Sybil verifier, which is joint work with Charles Kadir. So let's start with a very simple concurrent program where we have a shared variable x that is initially set to some constant n, and then we have two parallel threads that first acquire the same lock, then they read from x, then they write back what they read from x plus 1, and then they release the lock. And so what we want to verify for this program is that x in the end is equal to n plus 2. And kind of the classical approach of how you would perhaps verify this is to write the program down as or model it as a transition relation with an initial state predicate, a predicate that describes the transitions from one state to the next, and a safety predicate. And now how you could verify by inventing an inductive invariant, which is a predicate that holds in the initial state, it's preserved under the next step predicate, and it's implying the safe states, or in other words, it's disjoint from the unsafe states. And unfortunately, there are a number of problems with this approach. The first is that by looking at this transition relation, we essentially lose all the structure we have in the original program, and making a programmer invent an invariant on the transition system is quite unproductive. And also doing the proof directly on the original program is rather complex. Even for the simple program, the invariant is, I think, at least as big as the transition relation. Now, an alternative approach might be that we look at simple program transformations. So what we could do is, first of all, recognize that both of these threads basically execute the critical section, so they are protected by the same lock. And so we can consider both of the threads to really execute atomically. And so we don't have to consider any possible interleavings of one thread being interrupted while it is in the critical section. And now what we can recognize now is that basically we don't care about the lock anymore. In some sense, we can transform the program to just say that x is atomically incremented by 1, and we don't have any interference during this increment. And now by maybe seeing that there's some symmetry in this program, or that it does not really matter which thread goes first, we can transform it to a completely sequential program by just saying, okay, we just write one thread is going first and the other one going second. And now we really end up with a completely sequential program for which we can just generate a verification condition and really give it to an SMT solver that is hopefully able to automatically prove this program. And you might think that this exercise is kind of, silly for this simple program, but this is really just the tip of the iceberg. And what we are really interested in is proving realistic implementations of large concurrent systems, where the task of specification and proving really very quickly explodes in complexity. And so what our goal is, or what we really advocate with the civil verifier, is to do layered refinement over structured concurrent programs. So what I mean by that is instead of proving a program, like a low-level implementation of a program directly, we rather look at a number of transformations of this program. So we have like program 1, program 2, up to program n, where each of these steps does some small transformation to make the program simpler. So there is some connection between these programs, there's some properties preserved, but each of these transformations is rather small and simple to justify. Like it might need some invariant, but this invariant is much simpler than proving the low-level implementation directly. And each of these transformations should be supported by automated reasoning. So a programmer could say what the transformation should be, but then the tool should automatically say that this step is actually a valid transformation. Now, a crucial feature or design choice of the civil verifier is that each of these programs remains structured. So it's so the programmer never really sees a transition relation, but keeps working with procedures, imperative code, and calls to atomic actions, procedures, and so on. And the state transformations in the language are all encapsulated in what we call gated atomic actions. Like here, I'm showing a specification of a compare and swap operation on some variable x, or on the right, I'm showing the specification of a release of a lock, or you could even imagine a very high-level specification, like if you want to verify consensus protocol, then an atomic action for that you want to prove might be that you reach consensus in a single step. So there's just the decision reached in a single step that is consistent. And so the language really supports writing down low-level implementations with primitives that are supported by the platform you're interested in, and very high-level specifications that you want to prove. And finally, what Civil supports is an input language that actually lets you write all these layers of a program in a single syntactic artifact. So you don't have to basically repeat all the shared things between this individual programs, but you write one program from which all of these layers and their connection can be automatically extracted. So in the first part of my talk, I'd like to show you some of these transformations that you might use to connect different program layers, and then in the second part, I'm gonna get back to this issue of expressing many layers in a single syntactic artifact. So the first tactic that you have in Civil is the creation of these atomic blocks that we already saw in the introduction example, where we have this acquire and release of a lock and some reads and writes, and we want to say that we actually don't want to consider any interference in this thread. And the way Civil justifies this is by using a theory of commutative actions or mover types. So the programmer associates these mover types, like acquire being a right mover, release a left mover, and the lock protected reads and writes being actually both left and right movers. And now applying a reduction theorem like Litton's reduction that basically says if you have a sequence of left movers followed by a sequence of left movers, you can always rearrange this execution such that you see the block that the thread executes as atomic. And so what Civil has to do to justify this is first of all check that that the annotations that the programmer gave are valid. So what it does is basically taking each pairs of atomic actions and check that the mover types actually are valid, which is a logical condition. And the other thing is to check that the sequence of instructions that that appear in the program actually match the one that is supported by the reduction theorem. Now, another tactic is to create atomic actions from more complicated procedures. So the example I'm showing here is a very simple implementation of acquiring a lock, where we have a shared Boolean variable, and the acquiring of the lock is just implemented by repeatedly executing a compare and swap and trying to set B from false to true. And we basically keep repeating this until we actually succeed. And what we want to prove here is that this actually matches an atomic action that just blocks until B is false, and then it atomically sets a B to true. And the challenge here is that this procedure can be really interrupted in a number of places by other threads, and we have to take into account interference. And now what Sybil has to do to actually justify that this complicated code with a number of instructions can be replaced by a single atomic action is that all the behaviors that this procedure can have actually match the behavior of skip action, which just leaves the state unchanged a number of times. Then in a single atomic step, there's the behavior of acquire, and then we again have skip, which leaves the state unchanged. And so the idea for this simple example is that we can have multiple failures of compare and swap, and then eventually, if some other thread releases the lock, the compare and swap succeeds, and we grab the lock. And so what we see here is that actually all the failed compare and swaps correspond to skip, because the compare and swaps fails if B is currently true, and it leaves it at true. And then at some point, when the compare and swap succeeds, we go from false to true, which really corresponds what the atomic action specification says. Okay, so yeah, so this is the basics of creating coarser atomic actions from more fine-grained concurrent code. But what we often want to do is actually also change the state representation when we do the creation of atomic actions. Like here, I'm showing the same implementation for acquire, but what we want to do here is derive a bit more general specification for this acquire, where the variable is called L, and it ranges over either being none, meaning the thread or the lock is not held, or it contains the thread ID of the thread that currently holds the lock. And now the challenge is that we first of all have to somehow align these two different state representations. And Sybil does this by actually allowing the programmer to write code that introduces the connection between these two different states. So when the programmer writes the implementation, he or she can also annotate by saying that there's additional state introduced. Like here, we have to introduce this additional parameter that the atomic action takes, which is the thread ID of the executing thread. And then we also add something called an introduction action that is added to the branch where the compare and swap finally succeeds. And here the programmer just says that in this case, the lock variable from the more abstract state representation should be updated. So basically, when compare and swap goes from false to true, L goes from none to some thread ID. And again, looking at this argument of justifying this replacement, one thing you might notice is that you actually need an invariant for this proof, which gives a connection between these two state representations, which is really what you would expect, that whenever the lock is held, it is equal to some thread ID, and if it's not held, like if B is false, then the L variable is equal to none. And this is particularly important to prove that the step when compare and swap succeeds matches the acquire operation. Otherwise, we could not really prove that. Okay.
So question?
Sure.
So would you typically just provide a kind of a refinement mapping or forward simulation or something like that to prove this? Would you ask the user to?
So this is all in the background. So I mean, the simulation relation is what's happening on the meta level of basically proving the soundness of the proof system. But what the programmer writes is just code that says how the state should be connected. Like one part is here an invariant that needs to be stated, and the other thing is writing code when exactly the idea is that on the most basic layer, the program does not contain this L, but then the idea is that when doing the proof, there's kind of an intermediate layer where the newly introduced state is added to the original program, and the programmer writes what the meaning should be, like when exactly it should be updated together with other state. And so maybe this is actually crucial here. So, I was writing these yield points here, which basically separate each kind of atomic actions. Like the idea is that like before and after every compare and swap, there is a yield, but there's actually none when talking about this operations that assign meaning to introduce state. So there's no context switch that you have to consider here. So you kind of update the more abstract state together with the concrete state update.
Okay, so you instrument with ghost state basically, and the system just proves that there's a refinement mapping.
Something like that. I mean, so I like to think about it that by this having this mechanism that you can introduce new state and hide state, that you basically get rid of this explicit notion of ghost state. But you can think of it like that. Yeah.
Okay.
Yeah, but the idea is that as soon as this new state is introduced in higher layers of the program, it's just regular states. There's no specific notion of ghost.
Okay.
Yeah. Okay.
Thanks.
So now moving on to a more kind of specialized tactic which is about verifying asynchronous programs. So here I'm just again showing a simple example where we have a shared variable x and an action add that can be invoked to add some natural number to x. And now we have some action that creates this asynchronous add action. So it creates add 1, add 2, up to add n. And now the idea, what we want to prove is that when this action finishes and all the asynchronously created tasks are done, the x should be just incremented by the sum from 1 to n. And the issue here is that if you look at this async sum action, is that there are many possible interleavings of how this adds can execute, and there are many intermediate states. And kind of specifying a classical invariant would be quite painful because you would have to consider all these intermediate states. But what Sybil can do is actually focus on one particular execution that just executes these add operations in order. So it first executes add 1, add 2, add 3, and so on. And in the background, it justifies that all of the other interleavings are in some sense equivalent using mover reasoning. So the only thing that the programmer has to do is provide an invariant that basically specifies the intermediate states of this single execution, which I'm showing on the bottom of the screen. So it might look a bit messy, but it's actually not that hard to understand. So the idea is that it just has to specify any of these prefixes of an execution. So it picks some value j between 0 and n and says that all the basically the sum from 1 to j was already added to x, and then we are still remaining with the add operations from j plus 1 to n, which is really just saying that we just reason about this single interleaving, and we can save ourselves the pain of writing an invariant that has to deal with all of the other interleavings.
So in this case, would they have to say that? I guess they have to say that add is a mover type, or like it's
add has to be a left mover, such that it can be basically rearranged, such that we can always rearrange the execution the way we want. So yeah,
the user has to specify that.
The user has to specify that, right? And
then it checks that is actually a valid assumption. Is that right?
Correct. Yes. So what the user specifies is that add is the left mover, and the intention that that this async sum should be replaced by sum using this invariant, and this is basically all that's needed to now check that that this is actually the case. And yeah, I mean this example is quite simple because add is just an unconditional mover. But if you look at more interesting distributed protocols, there is some extra machinery that you might have to invoke to do abstraction during this induction proof. And if you want, you can look at our PLDI 2020 paper, which, for example, shows how protocols like Paxos can be verified like that. Okay, so yeah, so these were just some tactics that are supported in Civil. I hope this gave some idea. And the one thing that is really the foundation between all the tactics is invariance and linear permissions that kind of work in the background are really the bread and butter of verification. And so one concept that we introduced in Civil is this notion of a yield invariant, which is both named and parameterized. And so the idea is that in a procedure, it will be explicitly attached to certain control locations. Like here, I'm having a simple procedure that does 2 increments, and it's attached both as a precondition, postcondition, and in between these 2 invocations. And so, the only thing I want to note here is that this basically gives rise to a number of tasks that Civil has to do. The one thing is to do kind of sequential verification, where we always have to show that that from assuming an invariant and executing some code fragments, the invariant is established at the next point. And we also have to do non-interference reasoning, which basically means that each of these declared invariants has to be checked or proven interference-free against code fragments in the program. And the really nice thing by factoring out invariants in this named and parameterized way is that we can really save a lot of SMT solver calls by parameterization, because we now declare certain invariants only once and then instantiate it for certain locations in the program as suited, and we only have to do the non-interference check once. Right. And one other important feature is the use of linear permissions. And I kind of brushed this under the rug a bit before, but to actually prove that this acquire and release operations for locks are movers, like that acquires a right mover and releases a left mover, we actually need to know that they are passing in different thread IDs. Like if these two thread identifiers could be the same, then commutativity would not hold. And so what Civil provides is a way to annotate variables as linear, and then there's a whole type system that checks that these annotations are correct. And without explaining all the machinery, the important thing is that it basically gives us disjointness invariance for free, meaning that in a number of verification conditions, we have to combine code snippets from different contexts. Like if we do a non-interference check, we take an invariant from somewhere and the code snippet from somewhere else, and we have to check non-interference. And we might want to know that certain variables are for sure disjoint or carry different permissions. Or in commutativity checks like here, we just take this atomic action declarations and without knowing how they are exactly called in the program, and we want to know that, for example, thread identifiers are different, and linearity gives us a very convenient and ergonomic way to get these invariants without explicitly declaring them and carrying them around and managing them.
So can you say again what's special about yield invariants? Are those just invariants that are attached to a particular proof application, or is there something more?
So, I mean, the important thing is that you factor out the invariant. Like you don't just write it directly at certain points in the program, but you like what happens a lot is that that there are invariants that are slightly different in different locations of the program. And the key here is to factor this out using parameters. And one other key thing is that these parameters can again be linear. So when a code fragment reaches a certain location, it can stash a linear value in this invariant, and then the non-interference check can know that a certain other code snippet cannot have the same value as stashed in the invariant.
Okay.
What do you mean by linear in this context?
So let's see. So how should I explain this? So the idea is that each linear variable is associated a set of permissions. Like so the thing is, like here I'm talking about thread IDs, but in like thread IDs are not really baked into Sybil. It's just one particular application where you can use linearity. And so the idea is that so global variables can be linear and they are active all the time, and then local variables can be linear, but they might, like if one linear variable passes a value to some procedure, then it loses the linearity privilege. It passed the permission on, or it might be that the procedure returns some linear permissions back. And so now the idea is that at each, like if you would interrupt the program at any point in time, then there is some notion of active linear variables in all of the stack frames of the configuration. And if you collect all of the permissions that are stashed in these variables together, then the property is that they must be disjoint. And so by this disjoint, using this disjointness property, you can encode a number of concurrency control mechanisms like thread IDs, but also barrier synchronization and so on. And yeah, this is really the machinery behind getting some properties for free.
So here you typically get, for example, that two thread ID variables are different.
Yeah, exactly. So you cannot have a concurrent acquire and release operation being executed with the same thread ID. Yeah. Right.
Because I guess the checker will see that both are active and are linear, so it will conclude they cannot be the same. Is that correct?
Yeah, I mean, the idea is that the caller who calls this acquire and release actions has to provide a linear parameter. And so the idea is that at some point you have to set up the whole system by saying that like when the program starts, there are a number of thread IDs that are linear in the beginning, and then they are passed to all the threads that are created. And the type checker ensures that these IDs actually cannot be duplicated, and two threads that are spawned can actually end up with the same value. Okay, cool. Yeah, so this is this really concludes the part about kind of proof tactics in Sybil. Now I want to get back to this issue about layering, where the idea really is that this whole chain of programs and their connections that we are constructing, that basically really constitutes the proof, should be expressed as a single layered concurrent program. And so the idea is that we have some notion of data layering that says which variables are active or live on a certain layer in the proof, and also control layering, which says what are the operations that are part of which of the layers. And the key is that we now really only express the changes between different layers, and we don't repeat things in the program that don't change. So remember that I was saying that these program transformations between layers are usually quite small and should be easy to justify, which kind of means that other parts of the program will be untouched. And so you don't want to always repeat this part when writing out programs explicitly. And yeah, before showing you actual Sybil syntax, I just want to say that the syntax is basically a conservative extension of Boogie, which is a language for a sequential verifier. And so what Boogie provides us is all the imperative language to write code, like assignments, if conditions, branching, loops, and so on. And a bunch of specification features like pre-post conditions, assertions, loop invariants, and so forth. And what Sybil adds to the syntax is a number of statements like asynchronous calls, parallel calls, and yield statements to basically express concurrency. And then all of the other syntactic extensions that we need are written as attributes, which Boogie already provides on basically all of the abstract syntax tree elements, which kind of makes it easy to extend the language. And it looks like that. It's like curly braces, colon, attribute name, and a certain list of parameters. Cool. And so, yeah, I will now just go step by step over the construction of a particular layered program. So first of all, we have this global variable L that I used for the log example before. And now here I'm showing you the code for the acquire and release atomic actions. And on a first glance, it's really looking like a standard Boogie procedure, but we have this right and left annotations, which basically serve double duty as saying that these are the mover types for these actions. And it's also just saying that it should be considered as an atomic action. Now, on the other hand, we have the procedure acquire that I also showed you already that does this compare and swap business. And this one is annotated with yield to just say that it is a yielding procedure, basically saying it's a concurrent procedure that we want to verify. And it has this refines annotation that says that what we want to prove is that this procedure can be replaced by the acquire specification. Okay, and the thing that really ties these two things together is so-called layer annotations. So maybe let's start at looking at the global variables. So on the one hand, we have this B variable, which exists from layer 0 to 1, and the L variable exists from layer 1 to 2. So kind of like layer 0 you can consider as the really executable program, perhaps, where you have an actual compare and swap implementation of the hardware. Then layer 1 is where we have this procedure acquire, and it's actually it's annotated with layer 1, which means that it's disappearing layer. So what we say by this annotation is that from going from layer 1 to 2, we want to do the proof that the procedure acquire behaves like its atomic action specification. And on the other hand, the atomic actions also have a layer range that say on which layers they exist. And the important thing is that overlapping layer ranges for atomic actions basically determines which actions have to be checked against when doing commutativity checks. So when you where you basically don't want to have all the atomic actions in the program live across all of the layers, because you might block some commutativity properties that you want to prove. Cool. So then this other thing that I was also explaining already is this call to what we call an introduction action. So this is this special atomic action that assigns meaning to freshly introduced state. So you see here that we have this this call to set L in the case compare and swap succeeds, which has just the purpose of giving meaning to the new state that is introduced at layer 1. Right. Then we have yield invariance. So it's written like that. So in this case, it's called lock-inf, and it's what I was also showing already, that B is true if and only if L is not equal to none, and we attach it to the procedure as both the pre and post condition, and also as a loop invariant. Good. And the last thing is the linearity of the thread ID variables that we need to add here, and in particular, it's necessary in this program to prove the commutativity of acquire and release. And yeah, not just as a final thing, you now might have another layer, let's say layer 2, that now makes use of the acquire and a release operation that I was not showing, but it's kind of similar. It would just set B from true to false, and it's doing something in its critical section, maybe doing this atomic increment, first reading and writing some shared variable X. And now the idea is that this happens now on a higher layer, like basically from layer 1 to layer 3. We prove that whatever this client of the lock is doing specifies some specification that we want to give to it. And basically, like what you see on layer 3 is that the lock, in some sense, completely disappeared. So the client of this client procedure does not really need to know that the low-level implementation was done using a lock.
So a higher number is a higher level of abstraction here?
Yeah,
or,
that's right, yes. Yeah, so we might in the future replace it by like symbolic names, which might be more convenient, but right now we have numerical values where lower number means more concrete and higher is more abstract. Yes. Okay. And to kind of get some confidence that all the features that we have and the way we do proofs in Civil actually are convenient for users, kind of the best evidence that we get is kind of anecdotal in the sense that both we, kind of the developers of Civil, constructed a number of significant examples and proofs, and also a number of researchers that are not part of the development team already used Civil to verify interesting programs like a race detector and concurrent data structures, or prototype implementation to verify weak memory programs. And yeah, just to give you a bit of intuition, I want to talk about, briefly want to talk about two of the major case studies. Like one is a concurrent garbage collector, which it has the purpose of collecting unreachable heap allocated objects in a language where the users don't explicitly manage memory. And so the idea is that this garbage collector is verified across 7 layers, where the lowest layer is really a low-level implementation that only makes use of the atomic CPU operations, like reading, writing, compare and swap, and so on. And in the first step, we use locks and read-write accesses to critical sections to protect certain accesses in the code. And then as a next step, we can use this lock-protected accesses to form more coarse atomic actions that are used in the barrier synchronization part of the algorithm. And in the next step, we reason about the coordination between the collector thread that is responsible for cleaning up the memory and possibly concurrent threads that modify memory. And basically, this part of the proof ensures that the safety of phase transitions of the collector. This collector is kind of like idle for some time, then it starts walking over the memory, looking for memory objects if they are reachable or not, and then at some point it sweeps the unused objects, and this is about the safety of this phase changes. Then at some point we do a transformation in the state representation where kind of gray objects, it's not really important what it means, but in the concrete implementation, they are managed in a stack, and we transform it into a set, which is now more convenient to prove a big atomic action that basically says that the whole root scan, like basically starting at pointers that the program has and looking at all the reachable objects, can be done in a single atomic step. And then in the end, the garbage collector is basically hidden completely, and the client is really left with just a bunch of atomic actions for atomically allocating objects, reading and writing fields to objects, and checking object equality. Okay, and the second example that I already talked a bit about is an implementation of the Paxos consensus algorithm. And so the idea here is that the low-level implementation uses primitives like sending and receiving messages on the memory and doing memory updates on single nodes in this network. And so here the proof is done over 3 layers, where the first step is has the job of creating a coarser event handle from these low-level implementations. And in this step, we also do a kind of state transformation that makes subsequent steps or the subsequent step easier. And basically what you can think of this middle layer as the level of abstraction that you usually see in like papers or textbooks about Paxos descriptions. And from that level, we can use this inductive sequentialization proof rule that I was kind of illustrating before to reason about the particular interleaving of the protocol, where basically rounds happen in isolation. So it's kind of like this protocol executes in rounds, and we can do a proof that that only considers executions that don't cross round boundaries. And so the benefit is that our invariant gets much simpler. Like compared to a flat invariant proof, we can basically cut away a large part of the invariant, and this is really the complicated part of the invariant that has to talk about overlapping rounds and also has a more complicated quantifier structure.
So in terms of sort of like human effort, do you have an estimate of how long these? So I mean, like writing the spec is sort of like something you'd have to do no matter what, but like in terms of human months or weeks, I don't know, like, is there an estimate of the proof effort for these that you know of? Or?
True. I mean, it's a bit hard to say. I mean, I cannot really remember how long it took us for this proof, but like one thing I can say is that all of the people that were involved in this project are not experts on distributed systems, right? So we all had to understand Paxos first, and actually doing the proof the way we did it actually helped us understand it better, because the completely asynchronous executions are quite tricky to understand, and by kind of getting this understanding that you can think of it in terms of simple executions, and then justify that all of the other executions are somehow equivalent, helped us in understanding the proof. And so yeah, this was nice. And one other thing to mention is that actually these two parts of the proof, like connecting the low-level implementation with this intermediate layer, and then doing which actually doesn't reason about the protocol at all. It basically just does a state transformation and creates a coarse atomic action. Was done completely separate from doing the actual proof of the protocol with this other proof rule, and it was done by two different people. So basically by agreeing on interfaces between layers, you can actually share the work between a number of developers, which is a nice feature of the layered approach. Okay, yeah, I'm seeing that I'm already quite over time, so I will just quickly go over this. So the implementation of Sybil is really also done in terms of injecting itself into the Boogie pipeline. So, like Boogie takes as input the Boogie program, it has a parser, type checker, VC generation, and then interacts with the solver. And what Sybil does is basically add two other passes to this whole pipeline. Like the first one is a type checking phase where it has to check that all the layers that the programmer specified make sense, that the sequences of mover types in atomic blocks is allowed by a reduction argument, and that linearity is preserved by assignments and so on. And the second one is really about kind of semantic checks. And so the idea is that in each of these boxes here, we create one or more sequential procedures that encode some verification condition. Like let's pick out the mover types. It basically creates for each pair of atomic actions that needs to be proven commutative, it creates a procedure that implements this check. And I actually prepared a slide to explain this. If you want to know more about it, I can explain it later in the discussion. But for now, let me just say that if you really want to understand all these transformations, one good thing to try is actually use this Sybil desugared file argument of the verifier, because it will spit out all of these encodings of concurrent code into sequential verification conditions to inspect and understand. And yeah, this already leaves me with my last slide, where I want to encourage you to actually try out Sybil. Like if you go to our website, you can find all the resources. And I think you can actually benefit from Sybil in a number of ways. Like if you have some protocol or program in mind where you want to try it on, this would be one thing. But you might also use it for implementing a verifier for some language that you're working on, and you could use Sybil as a backend. Or you might just want to use a particular component like commutativity checking or non-interference checking for a verifier that you're working on. So there are a number of ways that it can be a benefit to you. And yeah, with that, I thank you for your attention, and I'm happy to answer questions.
Yes, thanks for your talk. Very interesting. I liked it. We had a lot of questions already during the talk.
Yeah.
Not sure if anything's left. Let's see. Participants. No hands are raised. You can also just speak up if you want.
Yeah, so like I guess it's continuing my theme of questioning of how much burden is placed on the user versus automation. And so like the example you gave where you have this civil program and there's sort of like the program is written and then there are these like annotations. So for example, if you write those annotations incorrectly, like you get them wrong, you get some feedback, I guess. I don't know, would it say that either like, okay, your program is not correct, or
yes, yeah, that's a good point. Like, yeah, it's basically like, it's probably best explained on this slide. You know, you see that basically the whole proof system implemented in Civil is decomposed in all of these different checks that are like, some are more on the syntactic static analysis side, and some are more on the logic side, where you actually, you generate a logical verification condition that you give to an SMT solver. And for each of, like, if any of those fails, you get a quite targeted error message. Like if you screw something up in your layer, in your layering, it will tell you something specific. Like one example could be that you have an atomic action that references or accesses some global variable, but this variable actually does not exist on the layers where the action exists. So this would be an error, and it would tell you, no, you're accessing this variable, but it's not existing at the appropriate layers. And yeah, other things would be like if a mover check fails, like maybe show it now. Like this would be a boogie procedure that is generated for doing a mover check between this acquire and release actions that I already showed, which it actually gets some properties from linearity, which we already discussed. So it gets this property for free that thread ID 1 is different from thread ID 2. Then it starts by assuming the gate of the release action, so that it's currently holding the lock, and then the check basically it calls these two actions in sequence, and then it asserts that you can actually flip the order of these two actions. So what we assert here is actually the transition relation that is computed by swapping these actions and computing their transition relation. And so if this check would fail, it would tell you, commutativity between acquire and release failed, and this is a path or a path in the model of where the violation happens. And then you can analyze, like, am I missing something in my specification? Or like one thing that could also happen, depending on which logic and assertions you use, you could potentially also run into limitations of the SMT solver. And if you heavily use quantified formulas, then you might have to provide more help to the solver to discharge.
Okay, yeah, that was also my next question of do you run into decidability concerns with the SMT solver? But yeah.
Yeah, I mean,
obviously that's what like Ivy tries to solve this, and other tools, right? But it's I'm sure it's always just lurking there as a potential problem. But
yeah, exactly. I mean, the issue usually is that like if you have a working proof, then it usually, like, the verification time is very fast. But if you use a lot of quantified formulas and you have an error in your proof, then it could be that you run into termination issues. And what we have been doing is working on some techniques to provide kind of custom instantiations, like to give ways for the programmer to say what would be appropriate instantiations for quantifiers to use, and directly get it to the right parts of the proof. And yeah, I mean, if somebody wants to pick up a research problem, I think this would be like very interesting to work on kind of domain specific quantifier instantiation techniques, or ways for letting users conveniently specify help for quantifier reasoning. Yeah,
and then last question, and I'll stop. But the layers of refinement essentially also have to be intuitively like generated, I guess, by like a human. Is that right? Like you had like 7 layers.
Yeah, exactly.
Which is
Yeah.
like all these layers of abstraction that you have to sort of like, I guess, just come up with or know, have knowledge of enough of the protocol to sort of build those layers, right?
Yeah, I mean, this is the creative part, coming up with the proof outline and structuring the proof. Yeah, this is really what has to be provided as input, and once you have that, you get help of automation.
Thanks.
Okay, good. Then we're closing the talk part of FRIDA for today. We meet again on Friday, same time as today. If you're interested in talking to a few people here, just hang around, and depending on how many we are, I will assign us to random groups. Let's see how many people really stay. Okay, so I'll just, let's say I'll assign 2 random groups, and then after 20 minutes or so, we can come back to the general room and see who's left. Okay.
We lost a few more people.
I think now when they're in the breakout rooms, we don't see them here anymore. Yeah. So
that's our group.
It didn't assign us. Strange. Why not? How are we special in the view of? Okay, you pick a number, 1 or 2. Do you
2.
see? Do you see?
No, I just see you.
Do you have a button below for breakout rooms?
Yeah. So I guess I can join. Oh yeah, I can just join whichever. Yeah.
Which one? Which one will you join?
I guess I'll join 1.
Okay, good. And I'll join the other, and we meet here. Or I can send messages or something, I think.
Okay.
Okay.